Greetings, and welcome to an exploration into the mysteries of the cosmos, a journey through the vast, silent universe beyond our daily reach. I'm truly pleased to have you here, eager to embark on a voyage that might help you unwind, relax, or simply indulge in the fascination of the star-studded expanse above us. Perhaps your day has been particularly long and tiring, or maybe you find comfort in contemplating distant galaxies, luminous stars, and the quiet, awe-inspiring secrets that the universe holds. Either way, tonight's adventure is crafted especially for you. There's no need to prepare or do anything special at this moment. Just allow your body to settle into a comfortable state. Encourage your mind to gradually slow its thoughts and let your consciousness drift gently towards peaceful sleep. Because tonight, we shall be delving deeply into the very fabric of the universe itself. We won't focus on just one single galaxy or solitary star. Instead, our journey will encompass the entire, ever-expanding cosmos, an intricate, magnificent system that has been unfolding for countless billions of years. We will take slow, careful steps from one fascinating fact to another, learning about phenomena such as black holes, those mysterious regions where gravity becomes so intense that nothing, not even light, can escape, and ancient light, which has traveled across the universe for billions of years before reaching us. We'll explore dark matter, the unseen mass that holds galaxies together, and take a closer look at some of the distant galaxies whose light has taken unimaginable spans of time to arrive here. You might discover that some concepts are startling and unexpected, while others will resonate quietly within your mind, lingering like a gentle thought at the very edge of sleep. If these calm, contemplative explorations bring you peace and help usher you into restful slumber, then may they serve their purpose. And if they do, you might find it comforting to let your awareness drift further, quietly contemplating the wonders we've touched upon. Now, if you're feeling ready, let's start this cosmic journey. The universe itself might be much older than recent calculations suggest. Currently, the most widely accepted estimate puts the age of the universe at approximately 13,800,000,000 years. This precise figure comes from detailed measurements of the cosmic microwave background, the faint afterglow of the Big Bang, and from observing how rapidly the universe is expanding over time. Yet, despite this consensus, different methods of measurement have led to slightly varying results. Some scientists studying ancient stars, distant galaxies, and the large-scale structure of the universe have proposed that the universe could be even older than this estimate implies. There are also questions about whether the rate at which the universe expands, known as the Hubble constant, is accurately measured, or if dark energy, the mysterious force driving acceleration, might itself be changing over cosmic time. These discrepancies have yet to be fully resolved, and although most astronomers continue to accept the approximate age of 13.8 billion years, the ongoing debates hint at deeper mysteries. Could it be that the universe is, in fact, older than we think? Or perhaps our understanding of its origins has yet to reveal fundamental truths. It's conceivable that what we perceive as the universe's beginning is just one chapter in a longer, more complex story, one that defies simple explanation. Beyond its age, the universe contains countless wandering worlds, rogue planets that drift through the cosmic void, unbound by the gravitational ties to any star. Not every planet is locked in an orbit around a luminous sun. Some are entirely free-floating, wandering aimlessly through the galaxy without the warmth or light of a parent star. These rogue worlds may have been formed through the usual process of planetary creation, only to be ejected from their original star systems due to chaotic gravitational interactions. Others may have originated independently, similar to failed stars, never attaining enough mass to ignite nuclear fusion. These solitary planets are dark, cold, and elusive, rarely seen directly unless they happen to pass in front of distant stars, casting faint shadows or glowing faintly in the infrared spectrum. Astronomers currently estimate that billions of such rogue planets traverse the Milky Way alone, and perhaps their numbers even surpass the total count of the galaxy's stars. Each one represents a silent, solitary sphere, a world adrift in the boundless darkness, spinning quietly amid the vast emptiness between celestial bodies. There are no sunrises or sunsets for these worlds, only endless nights broken occasionally by the distant glimmer of starlight illuminating their dark surfaces. The universe may also be a cycle of continual renewal, an infinite process of rebirth and transformation. The dominant cosmological model describes a universe that originated with the spectacular event known as the Big Bang and has been expanding ever since, possibly forever into the future. However, alternative theories propose a more intricate picture, one where the cosmos undergoes infinite cycles of expansion and contraction. In these models, the universe does not simply fade into cold darkness or end in a catastrophic crunch. Instead, it experiences rebirth, bouncing back from one phase to another. After expanding, many scientists propose the intriguing idea that the universe might not possess a definitive beginning or an ultimate end, but instead may be characterized by an ongoing, rhythmic cycle stretching across incomprehensible expanses of time. This perception envisions a cosmic dance in which one universe continuously gives rise to another, creating an infinite series of cosmic rebirths, each universe seamlessly transitioning into the next, in an eternal sequence that defies our conventional understanding of time and origin. Such an eternal or cyclic model suggests that the cosmos is not a one-time event, but an endless flow, a grand rhythm echoing through the fabric of space-time itself, extending beyond the limits of human comprehension. The earliest light that we can detect, often described as the oldest observable signal in the universe, originates from a time approximately 380,000 years after what is traditionally called the Big Bang. Before that pivotal moment, the universe existed as an almost unimaginable soup of intensely hot, dense energy, a glowing fog so luminous and compact that photons, the particles of light, could not travel far without scattering in different directions. In this primordial state, the universe was opaque, preventing light from escaping freely and making it impossible for us to peer back further in time through electromagnetic signals. However, a critical transition eventually occurred. As the universe expanded, it cooled down. This cooling reached a crucial threshold, allowing atoms, mainly hydrogen, to form out of the primordial plasma, causing the thick fog to gradually part and luminance to be released. It was at this point that photons were finally able to travel unhindered through space, delivering a faint but persistent glow, an ancient relic known today as the cosmic microwave background radiation. This primordial light, now stretched into long, cool microwave wavelengths by the ongoing expansion of space, continues to fill the universe, serving as a faint whisper from its earliest moments of transparency. The photons we detect as this cosmic microwave background have been journeying through space for more than 13 billion years. Their wavelength has been stretched from the original high-energy radiation into the microwave range, forming a delicate uniform background that offers us an extraordinary glimpse into the universe's nascent days. Although faint and subtle, this omnipresent glow embodies the memory of the universe's earliest clarity, a silent messenger carrying invaluable information about the initial conditions that set the stage for everything we see today. Turning our gaze inward to planetary systems, there exist some astonishing worlds with unusual and extraordinary compositions. For instance, certain distant stars host planets composed almost entirely of diamond. In these peculiar systems, the chemical makeup diverges significantly from what we are accustomed to on Earth. When a planet forms in a region where the abundance of carbon exceeds that of oxygen and the surrounding pressures are sufficiently high, a remarkable transformation can occur, one that results in a planet made predominantly of crystalline carbon. These extraordinary planets, often referred to as diamond worlds, are not merely theoretical. Astronomers have identified at least one promising candidate. This candidate is a highly dense planetary body orbiting a pulsar, a type of neutron star that emits regular beams of electromagnetic radiation, often the remnant core of a once massive star that has undergone a supernova explosion. Based on its mass, density, and composition, this distant planet is likely a colossal crystalline deposit, a planet essentially forged from giant diamonds. While these colossal diamond planets lack the shimmering brilliance we associate with gemstones, being far too hot for any sparkle, they evoke profound fascination because of their incredible makeup. Beneath the planet's scorching surface, immense and complex networks of carbon lattices could stretch across thousands of kilometers, creating a crystalline landscape of super-hard material that would awe any scientist or astronomer. Such worlds are exceedingly rare in the universe, but their existence serves as a vivid reminder that the cosmos is a place of extraordinary diversity and strange phenomena. In the universe's vast inventory, there are planets made of rocks, planets composed mainly of gases, and, quite astonishingly, planets that are essentially gigantic, crystalline structures of carbon. Worlds that challenge and expand our fundamental understanding of planetary formation. Contemplating the overall shape of the universe, many believe that it might possess no definitive edge, no boundary where space simply ends. Instead, it could be infinite, or, at the very least, possess a form of constant curvature that conceals its true extent. It is tempting for us to imagine the universe as something with clear borders or edges, like an enormous, boundless landscape that we could reach one day if we traveled far enough, reaching what seems like a limit or a border. Yet, the intricate laws of space and time, as described by Einstein's theory of general relativity, suggest a different reality. According to these laws, the shape of space is intimately influenced by its content, by the distribution of matter, energy, and gravity throughout the cosmos. Current scientific evidence does not support the idea of a finite universe with edges. Rather, it hints that the universe may be either truly infinite, a boundless expanse with no boundary, or, alternatively, so curved and expansive that it loops back on itself in a complex, seamless shape. It is entirely possible that a mysterious celestial body still exists beyond our current view, quietly orbiting the galaxy along a completely different trajectory, hidden from our instruments and sightlines. remaining invisible to our telescopes and detectors. Some scientific hypotheses even propose the existence of a twin star, often colloquially referred to as nemesis, which is linked by theorists to some perplexing patterns of mass extinctions observed throughout Earth's history. Although these connections lack definitive proof and remain speculative within the scientific community, they continue to inspire intriguing discussions about the possible unseen influences lurking in the vastness of space. The notion persists that our sun, so steady and singular when we observe it from Earth, might once have shared its birth with a silent, enigmatic companion, an ancient star that has long since vanished, swallowed by the cosmic darkness, leaving only faint traces of its existence among the stars. Visualize, for a moment, a raindrop composed of neutron star material. Such a drop would be unimaginably dense, weighing more than Mount Everest itself. Neutron stars are remnants, collapsed cores of gigantic stars that have undergone cataclysmic supernova explosions, leaving behind incredibly compact objects. These stellar remnants are diminutive in size, often just about 20 kilometers across, yet their mass surpasses that of our Sun. The density of matter within them is so extreme that a single teaspoonful would carry the combined weight of billions of metric tons, an almost incomprehensible concentration of matter in a tiny volume. Imagining a single droplet of neutron star material falling through our atmosphere is akin to contemplating a substance far heavier than any mountain found on Earth. Such density fundamentally contradicts everyday human experience, where atoms are normally spaced far apart. In these extraordinary conditions, atoms undergo dramatic transformations. Electrons and protons fuse into neutrons, creating a superfluid-like neutron soup, a state of matter that defies normal physical intuition. Neutron stars are some of the universe's most extreme objects. Small, dark, incredibly heavy, and capable of spinning at astonishing speeds. Despite their quiet, unassuming appearance, they bear the scars of stellar death, massive explosions and subsequent collapse, an astronomical memory embedded in their dense cores. These remnants exist in a state where matter is so compressed that gravity itself takes center stage, almost as if matter has become predominantly a force of its own. Meanwhile, when we look at the night sky and observe light coming from distant galaxies, we can sometimes detect that the signals have arrived through multiple routes. Light, unlike our usual expectations, does not always travel in a perfectly straight line. In regions of space where gravity is particularly intense, near massive clusters of galaxies, for instance, the fabric of space-time itself becomes curved and warped. This curvature bends the paths of passing light rays, similar to how a glass prism bends and distorts light beams passing through it. This phenomenon, known as gravitational lensing, produces some of the universe's most fascinating visual effects. One of its most astonishing consequences is our ability to see multiple images of the same distant galaxy, viewed from different angles, all owing to the different paths light has taken. These images can appear as elegant arcs, faint smudges, or even perfect rings, sometimes called Einstein rings, formed by the bending of light around massive objects. These aren't duplicates of the galaxy that exist elsewhere in space. Rather, they are multiple images created by different light pathways converging on our telescopes. It's as if the universe acts as a giant cosmic mirror, reflecting the same object in several places, depending on how the light has been bent by gravity. In some extraordinary cases, astronomers have observed individual supernovae, the explosive deaths of stars, exploding more than once, with the subsequent light signals arriving along different gravitational routes, creating multiple glimpses of a single event. These occurrences serve as a subtle yet profound reminder of the universe's complex geometry. Even the brightest light particles can become lost, diverted, or delayed on their journeys through the warped spacetime, ultimately finding their way back to us after their convoluted voyage. Turning our gaze toward the earliest chapter of cosmic history, it's theorized that the birth of the first stars was a far more luminous affair than the stars we see today. These primordial beacons might have blazed with a brightness a million times greater than that of our sun, illuminating the universe in its infancy. Such stars, known as population 3 stars, were unlike anything we observe in our current universe. They formed directly from the primordial gases of hydrogen and helium that remained after the Big Bang, the universe's fiery birthplace. These stars likely had no metals, elements heavier than helium, and as a result, they grew to enormous sizes, scorching hot and burning their fuel at an incredible rate. Some of them could have been hundreds of times more massive than our own sun. Their intense nuclear fusion processes caused them to shine with a brilliance that outshone our current stars by a factor of 1 million, albeit for a very brief cosmic lifespan. Their rapid, fiery lives lasted only. The light that once illuminated their presence has long since faded away, yet the traces of their existence continue to echo throughout the vast tapestry of the universe. These remnants, subtle fingerprints, can be found etched into the very fabric of ancient gas clouds that drift lazily across the cosmos and embedded within the silent, stable structures that mark the earliest moments of the universe's formation. Deep within the depths of space, amidst the cold darkness, flows a mysterious form of matter known as dark matter. This elusive substance surges through your body as you rest peacefully during sleep. As your body remains motionless, dark matter moves quietly and invisibly around you, an unseeable current woven into the fabric of space itself. Unlike ordinary matter, it does not shimmer, reflect, or emit light. It neither absorbs nor scatters photons. Instead, it exists in a form that's invisible to our eyes, yet possesses mass, making it responsive to the pull of gravity. Our galaxy, the grand spiral we call home, is enveloped by a vast spherical halo comprised mostly of dark matter. As Earth journeys through this immense halo, it is believed that trillions of dark matter particles pass through every square centimeter of our planet's surface each fleeting second. These particles do not collide with the atoms that compose our bodies, nor do they leave behind any direct traces or footprints. Yet, their ghostly presence is undeniable. They are ever present, silent spectators threading through the universe in an invisible, continuous flow. Without dark matter, cosmic structures such as galaxies would lack the gravitational glue necessary to hold themselves together. The intricate web of the universe's architecture would unravel, and galaxies would disperse into chaos. The formation of clusters and superclusters would be impossible, and the universe would look markedly different from what we observe today. Despite decades of research, the true nature of dark matter remains one of the greatest mysteries in cosmology. We do not yet know what it is made of. If it is composed of particles, some exotic form of matter, or something entirely different. However, what is clear is that dark matter is an integral part of our world. It passes through us silently and uninterrupted, constantly shaping the universe even as we sleep, unaware of its presence. Meanwhile, in the outer reaches of the cosmos, astronomers have made the startling discovery of galaxies that shine with an eerie, ghostly glow, despite having an astonishingly small number of stars. These peculiar systems, barely lit by stellar fire, are filled primarily with gas and an abundance of dark matter. They have little to no evidence of recent star formation, which raises intriguing questions about their history. Some of these galaxies may have been stripped of their stars through violent gravitational encounters with other massive objects, perhaps during close passes or collisions. Others might have never been prolific star producers, forming only a handful of stars, or perhaps none at all, over cosmic timescales. A few such galaxies are so faint that they are nearly invisible to the naked eye, detectable only through observations at certain wavelengths of light, revealing faint smudges beneath the darkness in deep sky surveys. These dim, elusive formations challenge our traditional understanding of how galaxies come into being and evolve. If they are rich in dark matter, why haven't they converted that material into stars? If they did contain stars in the past, where did those stars go? These enigmatic silent systems drift through space like the skeletal remnants of galaxies long gone, serving as quiet reminders that not every galaxy is bursting with bright, luminous light. Some exist in the shadows, unnoticed and unanswered by our current theories. Another puzzling feature of our universe is a region within the cosmic microwave background, the faint, pervasive afterglow of the Big Bang that defies expectations. This particular patch of sky, known as a cold spot, is significantly colder than the surrounding regions, a discrepancy that starkly contrasts with our predictions. It isn't just a marginally cooler area. It spans hundreds of millions of light years and is conspicuously larger than our models of early universe physics would suggest. This anomaly remains a perplexing mystery. Some scientists hypothesize that it might be the imprint of an immense cosmic void, an enormous region almost devoid of matter and galaxies, whose presence distorts the uniformity we expect in the universe. Others muse about more exotic possibilities. Could it be evidence of the universe colliding with another, or perhaps a relic of some extraordinary event during the universe's infancy in the period of rapid inflation? So far, no explanation has been wholly satisfactory, leaving this cold spot as one of cosmology's most quietly unsettling riddles. It does not scream for attention like a glaring anomaly. Instead, it whispers softly, suggesting that perhaps our universe is more complex and mysterious than we have yet understood, a vast, intricate puzzle waiting to be solved. Adding to the cosmic intrigue is the slow, inevitable retreat of the moon from our planet. Every year, it drifts away at a pace of about 3.5 centimeters, roughly the same distance as a fingernail grows in a single. In earlier epochs of our universe's history, the concept of time itself felt quite different. A day on Earth, for instance, was not the familiar 24 hours we know now, but rather just a few hours long. This peculiar reality can be attributed to the process known as tidal friction, a subtle but persistent force that subtly influences celestial dynamics over vast stretches of time. To understand it, imagine the moon exerting a gentle but constant tug on Earth's vast and swirling oceans, causing their waters to rise and fall rhythmically. As our planet spins on its axis, the gravitational pull from the moon creates a tidal bulge, which slightly lags behind directly beneath the satellite itself due to Earth's own rotation. Over countless ages, this lag results in a gradual transfer of energy from Earth's rotation to the Moon's orbital motion, causing the satellite to drift slowly away from our planet, an imperceptible process in human lifetimes, but one that accumulates inexorably on geological timescales. This transfer, driven by tidal friction, is a gentle, relentless force that, over eons, can lead to profound changes. Earth's rotation slows, and the Moon's orbit expands. Looking far into the future, it is conceivable that Earth and its lunar companion might reach a state of mutual tidal locking, whereby each body continually shows the same face to the other, forever harmonized in synchronized rotation. Until that distant day, however, the Moon continues its slow retreat, slipping outward day by day as our planet continues its effortless, continuous spin beneath the dim glow of its satellite companion. The universe, in its complexity, hosts a remarkable variety of celestial interactions that echo these gentle, intimate exchanges. One intriguing phenomenon occurs within binary star systems, where two stars are gravitationally bound and orbit one another in a cosmic dance. In some instances, these stellar pairs are so close that their outer layers, regions of loosely held gases and plasma, appear to touch or nearly touch. As these stars evolve, their mutual gravitational pull can cause one star to swell dramatically, sometimes dramatically enough to spill material over into its companion. This creates a delicate, spiraling exchange, a cosmic ballet involving streams of matter flowing back and forth. This process can proceed in several ways, sometimes calmly and steadily, with a gentle transfer of material, other times punctuated by spectacular bursts of light as the infalling matter heats up and ignites energetic outbursts. In the most extreme cases, this interaction results in a complete merging of the two stars into a single, more massive entity. The physics underlying these stellar relationships is extraordinarily intricate, involving complex gravitational and nuclear processes, but the visual impression can be unexpectedly elegant. Picture two stars orbiting so closely that their outer atmospheres brush against each other, their gravitational fields intertwined, their fates intertwined as well. In some scenarios, the smaller star becomes stripped down to a hot, dense core, glowing with residual nuclear energy, while its companion becomes swollen and enriched with additional material. Such interactions are not merely academic curiosities. They are fundamental to understanding some of the universe's most extraordinary objects, including certain supernovae and neutron star pairs. These binary systems are, in effect, natural laboratories illustrating how celestial bodies can interact, share, and transform each other's fate, ultimately revealing that even at the grandest scales, stars are not isolated entities, but part of a vast, interconnected cosmic web. Sometimes, these seemingly quiet interactions set the stage for catastrophic events, like giant stellar explosions or the formation of ultra-dense remnants, reminding us that the universe is full of surprises and complexity, often hidden beneath a serene surface. Contrary to the common perception of the cosmos as a vast, silent void, deep space is far from being an empty, lifeless expanse. Even in regions so distant from any star or galaxy that it appears utterly dark and devoid of matter, the universe remains teeming with activity on an almost unimaginably tiny scale. According to the principles of quantum physics, what we perceive as the vacuum, a perfect emptiness, is actually a dynamic and restless arena. In this environment, pairs of particles and antiparticles flicker into existence spontaneously from the quantum foam, only to vanish moments later. These quantum fluctuations are a fundamental feature of reality, constantly occurring everywhere and at all times, forming a subtle, invisible background hum beneath the apparent silence of space. This ubiquitous quantum activity can influence the motion of particles, affect the behavior of fundamental fields, and even contribute to the overall energy density of empty space. In fact, this restless energy is believed to underpin the mysterious phenomenon known as dark energy, an elusive force that is causing the universe's expansion to accelerate at an accelerating rate, gradually pulling everything in the cosmos further apart over billions of years. When we imagine deep space as a vast, silent, and still void, it is only a superficial impression. Underneath that calm veneer lies a complex dance of probabilities, a continuous, unseen symphony of particle creation and annihilation, a hidden hum that sustains the fabric of reality itself. Furthermore, the nature of time is. The notion I am about to explore may sound highly speculative, yet it opens up a realm of intriguing and almost surreal possibilities about the very fabric of our universe. In a cosmos governed by the principles of relativity, the nature of time itself becomes malleable, no longer an absolute, unwavering constant as one might intuitively imagine. Instead, time can stretch, elongate, slow down, or even bend, subtly shaped by the nature of the space through which it moves. This concept challenges our everyday understanding of temporal flow and invites us to consider a universe where the passage of time may vary depending on the structure of the region in space and the relative motion prevailing there. Focusing our gaze on our own galaxy, the vast and luminous Milky Way, we discover that it harbors a hidden, almost secretive halo that extends far beyond what our eyes can directly perceive. When we observe images of the Milky Way, what stands out clearly is its striking spiral shape, illuminated by countless stars, dust clouds, and glowing gas tucked into luminous arms winding gracefully around its core. Yet, this gorgeous, familiar structure is only part of a much larger and more complex entity. Encircling the visible disk of our galaxy is an enormous, mostly invisible component known as the galactic halo. This halo forms a vast spherical shell that encloses the galaxy, composed primarily of diffuse gas, dark matter, and remnants of ancient star clusters. It stretches outward into space, reaching distances many times greater than the diameter of the galaxy's luminous disk itself, effectively wrapping the Milky Way in an enormous, faint, and largely unseen envelope. Within this extended halo, astronomers believe reside numerous ancient star groups, clusters that have persisted since the early epochs of galaxy formation, along with wandering stars that are not confined to the galactic plane. Furthermore, the halo contains vast amounts of enigmatic dark matter, an invisible substance that exerts gravitational influences yet produces no detectable light. It is this unseen mass that helps keep the galaxy gravitationally bound and stable over cosmic timescales. The formation and evolution of this halo are influenced by the turbulent history of galaxy collisions and mergers, events that have shaped its structure and composition over trillions of years. Although we cannot detect the halo directly through conventional observation in visible light, we infer its existence with remarkable certainty by tracking the motion of stars within the galaxy and observing how light from distant objects bends as it passes near massive regions. These clues collectively suggest that the actual Milky Way is not just its bright spiral core, but is the luminous heart of a much larger, more diffuse cosmic structure, wrapped in an almost imperceptible cloud of dark matter and gas. Moving further outward in our exploration of the universe, we find that even the light from galaxies that formed shortly after the universe's earliest moments reaches us as a faint whisper from the distant past. The universe, as current scientific estimates suggest, is approximately 13,800,000,000 years old. Since light travels at a finite speed, around 300,000 kilometers per second, an unchanging cosmic speed limit, what we see in the night sky is not a direct, real-time view of current conditions. Instead, we observe galaxies as they appeared when the light first set out on its journey, often billions of years ago. As this ancient light travels through the expanding fabric of space, it becomes stretched and slowed, a process known as cosmological redshift, which shifts the light toward the red end of the spectrum. This stretching of light is precisely why our telescopes can glimpse into the universe's distant past, effectively allowing us to peer backward through time. Recent observations in astronomy have pushed our window even further, revealing light from galaxies that existed merely 200 million years after the Big Bang, the event that marked the birth of our universe. To put that into perspective, we are looking back to an era when the universe was still in its infancy, less than 1.5% of its current age, a cosmic blink of an eye. This light has been traveling toward us for more than 13.5 billion years, arriving here after a journey spanning unimaginably vast distances. The galaxy from which this ancient light originated is modest in size, faint in appearance, and considered primitive by astronomers because it possesses only the most fundamental structures of a galaxy, a small collection of stars, gas, and dust just beginning to form the first complex systems. Nevertheless, studying this distant galaxy offers invaluable insights into how the earliest cosmic structures coalesced from nothingness and evolved over time, providing a rare glimpse into the universe's earliest chapters, when darkness was slowly giving way to the first flickers of starlight, marking the dawn of a universe teeming with potential. On the grandest scales, the universe exhibits an astonishing and fascinating large-scale structure that resembles an intricate three-dimensional web. When astronomers meticulously chart the positions of galaxies across enormous stretches of space, spanning millions and even billions of light years, they discover a surprising, almost poetic pattern. Instead of a random scatter of galaxies, what emerges is a complex, interconnected network. Stars, despite their silent appearance in the night sky, are not entirely quiet. Beneath their luminous surfaces, they generate deep, resonant vibrations that travel throughout their vast interiors, akin to seismic waves that ripple through a planet during an earthquake. These pressure waves cause stars to pulse rhythmically and oscillate in subtle yet measurable ways. By meticulously observing tiny fluctuations in a star's brightness or monitoring the minute motions on its surface, astronomers can detect these internal vibrations. The scientific discipline dedicated to studying this phenomenon is known as asteroseismology, literally, the seismology of stars, where researchers interpret the faint tremors to unveil the hidden inner workings of celestial bodies. Every star possesses its own unique set of internal oscillation frequencies, much like a fingerprint that distinguishes one from another. These frequencies are intricately determined by multiple factors, including the star's size, its internal structural composition, and its stage of evolution. Through the art of listening to these cosmic vibrations, scientists gain a rare opportunity to peer beneath the star's surface and understand the complex processes occurring within. It's comparable to a form of celestial echolocation, an extraordinary method of hearing the music of stars across vast stretches of light years, even though this celestial symphony remains silent to human ears. Interestingly, some stars are believed to be older than the galaxies they inhabit. Since galaxies do not form instantaneously, but rather over an extended period through the merging of smaller galaxies and the continual accretion of stars and gases from surrounding regions, this results in a complex timeline. Certain stars within a galaxy can, therefore, predate the galaxy's current structure by several billion years. Some of these ancient stars are located either far out in the galaxy's outskirts or clustered in dense spherical groups known as globular clusters, which orbit at great distances from the galactic core. These stars have ages that exceed 13 billion years, almost as old as the universe itself, and serve as celestial fossils, silent witnesses to an era long before the galaxy had fully assembled. Their light whispers stories from a distant past, capturing events that unfolded before most of the universe's current structures even existed, bearing imprints of a universe that was far simpler in its early days, with fewer heavy elements and basic atomic structures dominating the cosmic landscape. Turning to another fascinating aspect of cosmic mysteries, astronomers have stumbled upon galaxies that challenge our understanding of the universe's invisible scaffolding, the elusive dark matter. Conventionally, dark matter is thought to act as an invisible glue, binding galaxies together, explaining why stars situated in the outer regions of galaxies move at speeds that seem too high to be sustained by the visible matter alone. It also accounts for the large-scale clustering of galaxies that we observe across the cosmos. According to prevailing theories, dark matter constitutes the majority of matter in the universe, though it remains undetectable by ordinary means. However, in recent years, observations have revealed systems of galaxies that seemingly defy this paradigm. These galaxies behave as if they contain no dark matter whatsoever. Their stars move as though only visible matter exists. No extra unseen mass influences their dynamics. Such discoveries were entirely unexpected and pose a significant challenge to existing models. Some researchers hypothesize that these unusual galaxies may have undergone past collisions or interactions that stripped away any surrounding dark matter. Or perhaps these findings hint that our understanding of dark matter itself needs refinement. Alternatively, it might suggest that dark matter isn't a universal component as once believed, but perhaps varies in its distribution or nature across different systems. Regardless of the explanation, these peculiar galaxies remind us that the universe still holds many secrets. They urge us to remain open to the possibility that the principles we consider universal, like the omnipresence of dark matter, may not be as all-encompassing as we once thought, indicating that there remains much to discover and comprehend about the cosmos. Meanwhile, our own sun is a magnificent example of internal vibrations at work. It resonates like a giant ringing bell, with sound waves rippling through its plasma interior. These waves, generated deep within the solar core, bounce back and forth across different layers, causing the entire star to vibrate in a highly subtle but persistent manner. Unlike the sounds that reach our ears, these are not audible to humans. They are pressure waves, traveling at frequencies far below what our ears can detect, making their direct perception impossible without sophisticated instrumentation. Thanks to highly sensitive instruments and observational techniques, scientists have succeeded in measuring these faint oscillations. They analyze the data to reconstruct details about the sun's internal structure, much like a doctor peering inside a patient using MRI scans. This branch of solar study is called helioseismology, a field that offers invaluable insights into the hidden layers of our closest star, revealing what lies beneath its glowing surface and helping us understand the fundamental processes powering it. In essence, whether examining distant stars, observing ancient celestial remnants, or deciphering the subtle vibrations within our sun, each of these studies exemplifies humanity's relentless curiosity about the universe. Through advanced techniques and innovative observations, we continue. By carefully studying the subtle patterns produced by the sun's oscillations, scientists are able to uncover a wealth of information about what happens deep beneath its luminous surface. These oscillations, often referred to as solar rings or oscillation modes, act like a window into the solar interior. Through precise measurements of how these ripples change over time, researchers can determine foundational properties such as the density and pressure inside the sun, its rotation at various depths, and even the intricate flows of superheated gases well hidden from sight. In many ways, the sun functions much like a colossal musical instrument, vast, intricate, and constantly producing a symphony of vibrations and sounds. To understand this celestial orchestra, scientists rely on very sensitive instruments capable of capturing these subtle signals, allowing us to listen to the sun's hidden melodies. The information gained from these observations not only enriches our understanding of our own star, but also offers critical insights into the workings of stars throughout the universe. On a grander scale, the universe presents an even more astonishing puzzle. Galaxies are not scattered randomly, but are interconnected through an immense network of filaments, massive, thread-like structures that weave the fabric of the cosmos. These filaments are composed of an elusive substance called dark matter, which does not emit, absorb, or reflect light, making it invisible to us with current technology. Over the course of billions of years, dark matter has coalesced into enormous sprawling filaments that extend across vast stretches of space. These cosmic strands serve as the scaffolding upon which galaxies form and evolve, guiding their movements much like beads threaded onto a cosmic string. Although we cannot see these filaments directly, we can infer their existence through the ways galaxies tend to cluster and align themselves along these unseen structures. Additionally, the bending of light, gravitational lensing, provides a powerful tool to map out the distribution of dark matter, revealing how these filaments connect enormous galaxy clusters separated by hundreds of millions of light years. Between these sprawling cosmic highways lie enormous voids, regions of space that are almost devoid of matter, stretching across vast distances and highlighting the universe's complex, web-like topology. Dark matter filaments do more than just connect galaxies. They act as the hidden backbone that shapes the growth and distribution of matter across cosmic time. This unseen framework influences the paths along which galaxies travel and the way in which matter clumps together under gravity. Yet, despite understanding their large-scale effects, scientists remain uncertain about the fundamental nature of dark matter itself. It is an enigmatic component of the universe, massive, pervasive, and unseen, quietly holding the universe's structure in place without revealing itself. Its presence is almost like a silent architect, constructing the universe's grand design from a mysterious, invisible material that we have yet to fully comprehend. The universe's vast structure exists as an immense, unseen monument, quietly governing the cosmic scene without drawing attention to itself. In considering the universe's expansion, we encounter a fascinating aspect of space itself. It can stretch faster than the speed of light. Under normal circumstances, the rule of physics states that nothing can move through space faster than light, but space itself is not bound by this limitation. Immediately following the Big Bang, an event marking the beginning of everything, the universe underwent a rapid exponential expansion known as cosmic inflation. During this brief but dramatic period, regions of space were pulled apart at speeds exceeding that of light, not because objects were moving through space faster than light can travel, but because space itself was expanding at such an extraordinary rate. This process is akin to a giant, stretching rubber sheet, where points on the surface can recede from each other faster than light without violating any physical laws. Today, as we observe distant galaxies receding from us, it's not that they are speeding away through space, but that the space in between them and us is continuously expanding. As this expansion continues, some galaxies are moving away so swiftly that their light will never reach us, effectively making them vanish from our observable universe. An expansion that is neither violent nor chaotic, but gentle and relentless, stretching on beyond our ability to comprehend. Our solar system itself is engaged in a complex dance that traces a helical, spiral path through the vastness of space. It is often easiest to imagine the planets moving neatly around the sun in flat, circular orbits, an elegant dance orchestra in a harmonious plane. However, when we step back to view the broader picture, a far stranger and more dynamic process appears. The sun isn't stationary. It is in continuous motion as it orbits the gravitational center of our galaxy, the Milky Way. Moving at nearly 1,000,000 kilometers an hour, the sun's journey is a high-speed voyage through the dark, star-studded expanse. As the sun moves, the planets in our solar system follow suit, not simply circling the sun like static objects, but spiraling through space, trailing behind their parent star in a twisting, corkscrew-like pattern. This combined motion creates a mesmerizing spiral, a kind of cosmic. When venturing into the depths of the universe, beyond the familiar stars, distant planets, and sprawling galaxies, what you encounter is often described as a seemingly endless void, an expanse of profound emptiness. Yet even in this vast, apparently desolate region of space, there is a subtle, almost imperceptible warmth that persists. This warmth is measured at approximately 2.7 Kelvin, a temperature just a few degrees above absolute zero, which is the lowest possible temperature where all thermal motion ceases. This residual thermal energy originates from what scientists call the cosmic microwave background, a faint, delicate glow that remains from the universe's earliest moments. Essentially, it is the lingering afterglow of the Big Bang, a relic that has been stretched and cooled over billions of years as the universe expanded. This delicate radiation, almost like a quiet whisper in the fabric of space, permeates the entire cosmos, filling every nook and cranny without exception. Regardless of the direction in which you turn, this faint thermal signature is always present, an ever-present reminder of the universe's fiery origin. It is a gentle but persistent echo from the dawn of time, measurable even now, long after the universe has cooled and expanded. Looking into the future, this temperature will continue to decline, gradually approaching near absolute zero. Over an estimated span of countless trillions of years, the universe's temperature could get even lower, approaching the coldest limit conceivable, yet it will never quite reach it. Even in the vast, silent emptiness of intergalactic space, the remnants of heat, no matter how faint, still linger, an indelible mark of the universe's fiery inception. Beneath the grandeur and apparent chaos of the cosmos, the smallest scales reveal a realm of unpredictability governed by the peculiar rules of quantum physics. At dimensions far smaller than an atom, the universe behaves in ways that defy classical understanding, characterized by seemingly random fluctuations and fleeting phenomena. These tiny variations in energy, which can appear and disappear within an instant, are manifestations of the inherent uncertainty that quantum theory embraces. It is as if the fabric of reality itself is constantly trembling with ephemeral ripples, minute blips of energy that exist only briefly before vanishing into nothingness. According to many cosmologists, these minuscule and transient quantum events might have played a critical role during the universe's earliest moments. During an extraordinary event known as inflation, space itself expanded at an incomprehensible speed, far faster than the speed of light, stretching these minuscule quantum fluctuations to colossal proportions. These amplified irregularities laid the groundwork for the structure of the universe as we observe it today. They acted as the cosmic seeds from which galaxies, stars, and planetary systems would eventually emerge. In essence, the vast, sprawling universe, its intricate filaments, sprawling voids, and shimmering clusters, may all trace their origins back to fleeting, minuscule fluctuations that occurred in the primordial quantum foam, at the smallest conceivable scales. All of the complex and beautiful cosmic structures we see today are rooted in these ephemeral chance events, born from the trembling of what seemed like nothing at the universe's birth. Stars are not eternal beacons. Their life cycles are marked by periods of luminous growth and slow fade, resembling rhythmic pulses that echo across millions or even billions of years. Unlike a sudden, explosive death, some stars end their lives in a more gradual and subtle manner, emitting gentle, rhythmic variations in brightness. These stars, known as variable stars, follow a predictable pattern of brightening and dimming, almost like a slow, celestial heartbeat. Their cycles of expansion and contraction are driven by changes in their outer gaseous layers. When gases expand and cool, the star dims slightly, only to contract and heat up again, causing an increase in luminosity. The period of these pulsations varies widely among different types of variable stars, with some completing a full cycle every few days, while others take several months or even years. Astronomers have long harnessed these rhythmic patterns to measure vast cosmic distances, as the relationship between their intrinsic brightness and pulsation period serves as a reliable standard candle. These gentle, recurring pulsations also serve as poetic reminders that even in their death throes, stars continue to keep time, not with mechanical clocks, but with long, slow breaths that echo through the universe. Their rhythmic beating offers a quiet, steady rhythm to the cosmic symphony, a testament to the enduring, cyclical nature of stellar evolution. On an even grander scale, the Earth itself is enveloped within a colossal bubble of hot, ionized gas, an invisible, often overlooked component of our local cosmic environment. If one could perceive the universe beyond the limits of ordinary optical light, perhaps through special instruments tuned to wavelengths beyond human vision, they would discover that our solar system resides inside a vast, glowing cavity of ionized gas. This region, known as the local bubble, extends hundreds of light years in every direction, forming a sort of cosmic alcove within the Milky Way galaxy. Currently, our solar system continues its peaceful journey through a rather calm and sparse region of the galaxy's vast expanse. We are sailing through this particular zone with a gentle, almost imperceptible motion, surrounded by a faint, thin shell composed of hotter gas and dust particles. Importantly, this environment does not pose any danger to us. There are no immediate threats lurking within it. While we cannot feel its presence physically, it surrounds us invisibly, forming a quiet, almost serene buffer zone. This tranquil shell is a byproduct of ancient cosmic violence, a remnant from distant cataclysmic events long past, which has now settled into a subtle, calming backdrop that defines the neighborhood of our galaxy. Beyond this familiar, peaceful shell lies a region of space so vast and empty that it feels almost surreal. Situated behind the so-called Great Attractor, which is itself a mysterious and powerful gravitational anomaly, lies an immense expanse of near-total emptiness. The Great Attractor is a colossal concentration of mass, so massive that entire galaxy clusters, including our own Milky Way, are gradually being pulled towards it in a slow, relentless dance through space. It acts like a cosmic anchor, subtly influencing the movement of countless galaxies around it. Yet, behind this immense gathering of matter resides an even more puzzling zone. Known as the dipole repeller, this region is strikingly empty, so much so that it appears almost as a void, a vast gulf devoid of galaxies or matter. But this emptiness is not simply a gap with fewer galaxies. Instead, it is a gigantic cosmic cavity spanning hundreds of millions of light years in every direction. Surprisingly, its presence seems to have an active role in cosmic dynamics, as the emptiness appears to exert a repulsive effect, subtly pushing galaxies away from it. Together, the gravitational pull of the Great Attractor and the repulsive influence of the dipole repeller create a delicate balance, a quiet tug-of-war, that ultimately shapes the slow drift and motion of our local universe. This ongoing cosmic battle between the attraction of concentrated mass and the repulsion of emptiness is a vital part of understanding why our galaxy moves as it does. It's as if unseen hands are gently guiding us, pulling us forward with the unseen weight of mass, while the vast void behind acts like a cosmic brake, nudging away at the same time. This scenario reminds us that in the universe, both existence and absence are powerful forces, capable of influencing the path we follow through the endless dark. It's a constant, subtle reminder that the universe's motion is not just driven by signs of matter, but also by the large, silent spaces of emptiness that surround and shape it. On a more minute, but equally astonishing scale, trillions of particles called neutrinos advance silently through every inch of our world. At this very moment, an unimaginably vast number of these elusive particles are slipping through your body, passing through the Earth itself. Yet, beneath your skin, beneath your bones, you feel nothing. These particles are incredibly light and have no electric charge, which makes them nearly impervious to normal matter. They are constantly produced in huge quantities by the sun's nuclear fusion processes, by exploding stars in distant galaxies, and even during the fiery moments thought to have marked the birth of our universe billions of years ago. What makes neutrinos truly extraordinary is their ability to traverse matter virtually unhindered. They can sail straight through a planet or your entire body, leaving no trace behind. Only rarely do they interact with normal matter, and in those exceptional cases, scientists can detect these fleeting collisions using highly specialized instruments buried deep underground, shielded from other sources of interference. Most neutrinos, however, simply pass through without any disturbance, streaming through space and the universe's fabric at speeds approaching that of light. Despite their rapid journey through space and matter, their interactions with normal objects remain infinitesimally rare, making them silent, almost ghostly messengers from the distant cosmos. Next, consider the life cycle of massive stars, the titans of the universe. Under certain conditions, these enormous celestial bodies do not end their lives with a spectacular explosion, but instead take a dramatically different path. When the most massive stars exhaust their nuclear fuel, instead of detonating in a brilliant supernova, they can undergo a process known as direct collapse. In this scenario, the star's core implodes inward with such overwhelming gravity that there is no outward explosion, no fireworks, no bright farewell. Instead, the star simply shrinks and vanishes, collapsing directly into a black hole. This process occurs so swiftly and efficiently that the outer layers of the star plunge inward without any of the luminous display typically associated with stellar death. In these extraordinary cases, the stellar remnants are black holes, completely invisible, infinitely dense points in space that exert a tremendous gravitational pull. Astronomers have observed instances where stars seem to vanish without a trace, as if their glow simply flickered out in an instant, leaving behind only the black. Our own galaxy, the Milky Way, serves as a fascinating example within the cosmic realm, hosting not just stars, planets, and nebulae, but also numerous smaller satellite galaxies that orbit it in a complex gravitational dance. Among these, the most renowned and easily observable are the Large Magellanic Cloud and the Small Magellanic Cloud, which have been studied extensively by astronomers and captured in countless images. These satellite galaxies resemble tiny moons orbiting a grander celestial body, gently gliding along long, elongated, elliptical trajectories through the vastness of space, their paths etched over eons in the fabric of the universe. As they journey around the Milky Way, sometimes the larger galaxy's immense gravitational pull exerts enough influence to strip stars away from these smaller companions, creating splendid streams of stellar material that stretch across millions of light years. These stellar streams form intricate tidal tails, beautifully illustrating how the gravitational tug of a massive galaxy can shape the destiny of its smaller partners over cosmic timescales. In many cases, a smaller galaxy can be entirely absorbed by its larger neighbor, gradually merging into it, adding its stars and material to the grander galactic structure in a slow, methodical process that can take billions of years. These cosmic interactions, often described as slow, elegant dances, unfold on an unimaginably vast scale, highlighting the enduring and dynamic nature of the universe's evolution. Even in the deep tranquility of interstellar space, galaxies can exist in relation to each other, quietly influencing their movements and destinies, like silent companions sharing an infinite cosmic journey. Moving beyond the framework of galaxies, the universe reveals phenomena that are both awe-inspiring and incomprehensibly energetic. Among the most dazzling are the brilliant outbursts originating from collapsing magnetic stars, or neutron stars, which generate some of the universe's most intense explosions. Within this category lies a rare and extraordinarily luminous event known as a magnetar hypernova, a spectacular explosion that may rank among the brightest cosmic phenomena the universe can produce. To understand this, one must consider that a magnetar is a type of neutron star characterized by an unimaginably powerful magnetic field, trillions of times stronger than Earth's magnetic field. When a massive star exhausts its nuclear fuel and collapses under its own gravity, it can transform into a magnetar. If this collapse occurs rapidly and the magnetic energy is released in an intense burst, the resulting explosion manifests as a luminous, energetic flash, far more powerful than a typical supernova. These hypernovae are believed to be responsible for some of the universe's long-duration gamma-ray bursts, remarkable flashes of high-energy light that traverse the cosmos at astonishing speeds, outshining entire galaxies for mere seconds. Despite their fleeting duration, the gamma-ray emissions from these events can originate billions of light-years away, allowing us to observe the universe's most energetic and mysterious phenomena. These explosive bursts are produced by the rapid collapse of a tiny, dense object wrapped in an immense magnetic fire, collapsing inward in a cosmic implosion that unleashes tremendous amounts of energy. Such phenomena rank among the universe's most intense and spectacular displays, illustrating how a relatively small object, merely a few miles across, yet incredibly dense, can produce a flash of light so bright that it outshines entire stellar communities. In contemplating the universe's vastness, one must recognize that the edge of the observable universe is not the same as the universe's boundary itself. When we look out into space, what we see is limited by the distance that light has had enough time to travel since the moment of the Big Bang, roughly 46 billion light-years in every direction. This boundary, known as the observable universe, is not a literal wall or dividing line, but rather a horizon, an extension of our observational limits determined by the finite speed of light and the ongoing expansion of space. Beyond this horizon, the universe likely continues endlessly, filled with countless galaxies and stars that we cannot currently observe. Furthermore, because the universe's expansion is accelerating, certain regions are now receding from us at speeds exceeding that of light, due to the stretching of space itself. As a result, the light from these distant parts may never reach us, no matter how long we wait, making them forever beyond our observational reach. Therefore, the observable universe can be envisioned as a vast, bubble-shaped region of what is accessible to our view, a kind of celestial cloud that contains everything we can detect from our vantage point. Outside this luminous bubble, the universe continues unabated, potentially spanning an infinite expanse teeming with galaxies, stars, and cosmic objects yet to be discovered. This enormous, unobservable universe remains a tantalizing mystery, inspiring scientists to push the boundaries of understanding and explore the fundamental nature of reality. Within this cosmic landscape, some galaxies are remarkable for their ability to eject streams of ionized plasma, jets that can extend across millions of light years. At the heart of many of these luminous giants lies a supermassive black hole, weighing millions or even billions of times more than the most intense and energetic outflows known to astrophysicists are believed to originate from regions surrounding black holes, where gravity is so extreme that even photons, particles of light, struggle to escape their grasp. These outflows can unleash tremendous amounts of energy into space, reshaping their surroundings and influencing the formation of new stars and planetary systems. Interestingly, even the quietest phenomena, such as silence or stillness, seem to leave an impression in the vast cosmic landscape, as if the absence of sound or movement carries its own subtle signature. Within our galaxy, the Milky Way, there is a fascinating star that defies the common pattern of orbital motion. Most stars in the galaxy orbit the galactic center in a steady direction, following the overall rotation of the galaxy like cars moving along a well-established highway. However, at least one star, cataloged as H04375, Chittirista Tritsit Divid, moves in the exact opposite direction. Its orbit is retrograde, meaning it travels against the mainstream flow, much like a salmon swimming upstream against a rushing current. This unusual motion raises intriguing questions about its origins. One plausible explanation is that this star was once part of a smaller galaxy that was absorbed by the Milky Way in ancient times, and its orbit reflects its heritage from that separate, older stellar system. Alternatively, it might have been ejected from its original orbit through a cosmic slingshot maneuver, an intense gravitational interaction possibly involving a black hole or a dense cluster of stars, propelling it onto this unusual trajectory. Regardless of how it arrived there, this celestial wanderer serves as a quiet but profound reminder that not all stars conform to the grand, orderly choreography of our galaxy. Even within the majestic, clockwork universe, there are objects that break the rules, forging their own paths through the cosmic void. Turning our attention toward the core of the Milky Way, we find a region that, despite its darkness and mystery, offers intriguing hints about the complex chemistry unfolding in the depths of space. Imagine the central area of our galaxy emitting a scent reminiscent of ripe raspberries and dark rum, an image that might seem humorous or even fantastical, but it's based on real scientific observations. Although the space around the galactic center is a vacuum, devoid of air, and thus incapable of carrying smell in the way our noses experience it on Earth, astronomers have detected molecules that suggest a different kind of sensory experience. By analyzing the dust clouds near this busy hub, scientists identified a molecule called ethyl formate, which on Earth is known for its delightful aroma of berries and its association with the scent of aged rum. These discoveries do not mean that the galactic center genuinely smells like fruit or liquor. Rather, they reveal that the region hosts complex organic molecules, such as alcohols, sugars, and precursors to amino acids, that are fundamental building blocks of life as we understand it. These molecules are part of a rich chemical soup that pervades interstellar clouds, silently swirling between stars. While this chemistry isn't life itself, it demonstrates the kind of molecular complexity necessary for life's emergence, hinting at the profound processes occurring in the depths of space that could one day lead to the origins of life elsewhere in the universe. Meanwhile, our universe is not a static, quiet expanse, but a dynamic arena where grand cosmic events unfold on timescales spanning billions of years. One such event involves the Andromeda Galaxy, our closest large galactic neighbor, which is slowly making its way toward the Milky Way in a cosmic collision course. Currently, Andromeda is located roughly 2,500,000 light-years away, an unimaginably vast distance, yet its approach is inexorably closing that gap. Over the next 4 billion years, the gravitational pull between the two galaxies will intensify to the point where they will begin to merge into a single, more massive celestial structure. Interestingly, the outer regions of both galaxies, known as their halos, consisting of vast clouds of hot gas and mysterious dark matter, are already beginning to overlap and mingle, suggesting that contact has, in a sense, already started beyond the visible stars. The eventual union of the Milky Way and Andromeda will resemble a gentle blending rather than a catastrophic crash. Most stars will pass by one another without colliding, thanks to the vast distances separating individual stellar systems. Over time, these two spiraling galaxies will coalesce into one larger, more rounded elliptical galaxy, a process that could be affectionately nicknamed Milka in anticipation of this cosmic union. While assembling over billions of years, this transformation embodies the slow but relentless march of cosmic evolution, demonstrating that even the grandest galactic phenomena are processes of gradual change. And beyond these spectacular mergers and migrations, the universe itself continues to glow faintly with ancient light, playing a cosmic game of hide and seek. Surrounding you, wherever you are in space, is the omnipresent whisper of the cosmic microwave background, a faint, pervasive glow known as the afterglow of the Big Bang. This, since that initial burst of light was emitted, it has continued to traverse the vast emptiness of space, gradually stretching out and transforming into what we now recognize as microwave radiation, a process driven by the ongoing expansion of the universe itself. Today, this ancient light reaches us from all directions in space, presenting itself as a nearly uniform glow that pervades the cosmos. This diffuse background radiation is not something that can be seen with the naked eye, nor can we feel it physically. Instead, it can only be detected through the highly sensitive instruments of modern science, which perceive it as a faint, persistent whisper from the universe's earliest moments. This whisper is the most ancient light we are capable of observing, a subtle yet profound signal emanating from the universe's infancy, still echoing across the vast stretches of space and the unfolding tapestry of time itself. This primordial glow serves as a cosmic relic, offering us a glimpse into conditions that existed billions of years ago, shortly after the universe's birth, providing invaluable clues about the origins and early evolution of everything we see today. In the grand theater of cosmic phenomena, it is only natural to associate the brilliance of astronomical cataclysms, such as supernovae, with luminous explosions bright enough to outshine entire galaxies. These spectacular events occur when massive stars reach the end of their life cycle, collapsing under gravity and releasing an immense amount of energy in a flash that temporarily dominates the cosmic landscape. However, it is equally important to understand that not every supernova radiates visible light or manifests as a dazzling spectacle. Some supernovae are, in fact, what astronomers refer to as failed supernovae, stellar deaths that take a markedly different path. In these cases, a star's core undergoes gravitational collapse, forming a black hole, but the outer layers do not explode outward in a blazing spectacle. Instead, they may quietly spiral inward, feeding the newly formed black hole without the dramatic fireworks typically associated with supernovae. Occasionally, astronomers have observed stars that appeared stable and unremarkable, only to vanish suddenly and without warning, leaving no sign of a luminous explosion, no fading glow, just darkness, an almost perfect disappearance. Such events suggest that the star's core collapse was so complete that nearly all of its energy was devoured by the emerging black hole in silence. Although the process is violent on a fundamental level, most of the destruction is concealed behind a shroud of darkness, serving as a reminder that not all deaths in the cosmos produce noise or bright displays. Some unfold in quiet, unseen ways. Beneath the vast cosmic canvas, there exist entire galaxies composed predominantly of gas and dark matter, caught in the unyielding grip of gravity. When we picture galaxies, the dominant images that come to mind are often of luminous spiral arms shimmering with countless stars, or luminous elliptical forms glowing with accumulated stellar light. But the universe also hosts a more subtle and elusive class of galactic structures, whose faint and almost ghostly appearance makes them difficult to observe with ordinary telescopes. These dim and often overlooked systems contain very few stars, yet they still possess significant mass primarily in the form of gas and dark matter, forming gravitationally bound structures that are often terribly elusive. Due to their low luminosity, they usually appear only as faint smudges, subtle distortions in the cosmic background, or are inferred through indirect measurements such as gravitational effects on nearby visible objects. Some of these faint galaxies may be considered failed systems because they never successfully formed many stars during their evolutionary history, perhaps because early cosmic processes stripped away their gas supplies or heated the material to such high temperatures that star formation was effectively halted. Others might exist temporarily, representing transitional phases in galaxy evolution. What unites all of them is their understated and delicate nature. Devoid of fireworks or spectacular spiral arms, they quietly exert their influence through gravity, simply existing in silence. These galaxies serve as a poignant reminder that not every galactic entity shines brightly or commands the spotlight. Some remain in hushed obscurity, observable only through patient investigation and nuanced understanding. Meanwhile, the universe's most mysterious and powerful objects, black holes, are capable of engaging in dramatic cosmic dances involving the collision and merging of these dark giants. When two black holes become gravitationally bound to each other, spiraling inward over cosmic timescales, they produce ripples in the fabric of space-time known as gravitational waves. As these black holes draw closer and their orbital dance accelerates, they gradually shed energy in the form of these ripples, culminating in an extraordinary, final union that releases an enormous burst of gravitational energy. In this moment, the two unseen behemoths coalesce into a single, even more massive black hole, an event characterized by an incredible release of energy that is utterly invisible to conventional telescopes. Although no light is emitted during these mergers, the oscillations in space-time themselves propagate outward, rippling across the universe and reaching detectors on Earth. The first direct detection of such gravitational waves occurred in 2015, confirming a prediction that Einstein had smaller stars, much like our own sun, have a life cycle that unfolds at a much more leisurely and measured pace compared to their larger counterparts. Once fueled by hydrogen in their cores, they follow a gentle evolutionary path. As the hydrogen reserves dwindle, These stars gradually expand into what we call red giants, swelling to enormous sizes while shedding some of their outermost layers into space. This process of expansion, combined with material loss, culminates in the formation of a dense, extremely hot core known as a white dwarf. This remnant is essentially the exposed core of the original star, a compact ball of carbon and oxygen that no longer engages in nuclear fusion. Instead of generating energy through active processes, it simply radiates away the residual heat accumulated during its previous life stages, doing so at an almost imperceptibly slow pace. Over billions of years, a white dwarf's temperature decreases gradually, and the star's brightness diminishes correspondingly until it fades completely into an almost invisible state. This final stage is called a black dwarf, though, in reality, the universe so far isn't old enough for any white dwarf to have cooled enough to become a true black dwarf. Every white dwarf that has ever formed in the universe still exists in some form, quietly glowing in the dark cosmic expanse as it slowly cools. The process of their death resembles a gentle, prolonged ember, cooling rather than a sudden, spectacular explosion, emphasizing a sense of quiet, unhurried decline over the vast stretch of cosmic time. Moving beyond individual stars, the effects of gravity in the universe further illustrate the strange and fascinating nature of spacetime. Near a black hole, this influence becomes extraordinarily pronounced, leading to effects that challenge our everyday perceptions of time. According to Einstein's general theory of relativity, gravity does not merely pull on matter, but also causes the geometry of space and time itself to bend and warp. The stronger the gravitational field, the more significant this curvature becomes, dramatically affecting how time flows. In the immediate vicinity of a black hole, where gravity is at its most intense, the passage of time can slow down to a degree that seems almost surreal. For an observer orbiting just outside the black hole's event horizon, the boundary beyond which nothing can escape, their experience of seconds, minutes, or hours would be vastly different from that of someone far removed from such a gravitational beast. Minutes spent near the event horizon could correspond to years passing elsewhere in the universe. This phenomenon, known as gravitational time dilation, isn't science fiction, but a well-documented aspect of physics that has been confirmed through experiments. For example, precise measurements of GPS satellites orbiting Earth must account for this effect. In the case of black holes, where gravity is incredibly intense, the stretching or dilation of time becomes profound. Essentially, black holes don't just trap light, they stretch and bend the very fabric of time itself, creating a cosmic distortion that has fascinated scientists for decades. Turning our gaze to the vast reaches between galaxies, we find that these empty spaces are astonishingly cold, colder than any place on Earth, or within most laboratories. Far away from the warmth of stars, planets, or clouds of gas, the intergalactic voids remain among the most chilling environments known in the universe. Temperatures in these regions tend to hover just a few degrees above absolute zero, approximately 2.7 Kelvin, a temperature so close to zero that atomic motion virtually ceases. This extreme cold results from the near-complete absence of particles and energy in these enormous expanses. With hardly any matter to retain or generate heat, these regions are essentially empty, save for a sparse scattering of stray atoms and the faint afterglow of the universe's early moments. known as the cosmic microwave background. This residual radiation bathes the universe in a gentle, persistent glow, akin to a faint microwave hiss that persists in the background of the universe's quietest places. These vast, monotonous voids stretch across millions of light years, forming some of the deepest, most enigmatic shadows in the cosmos. They contain only the faint whispers of the universe's origin, remnants of creation's earliest moments, making them the loneliest and most desolate regions in the entire universe. In addition to these distant voids, the universe itself is in a continual process of becoming more transparent with each passing epoch. During its earliest moments, shortly after the Big Bang, the universe was filled with a hot, dense plasma composed of free electrons and atomic nuclei that strongly scattered light. As a result, photons, the particles of light, could not freely travel across space, rendering the universe opaque and stifling any direct observation of its distant past. However, as the universe expanded and cooled over cosmic time, it reached a key milestone known as recombination, occurring approximately 380,000 years after the Big Bang. During this epoch, free electrons combined with nuclei, forming neutral atoms, mainly hydrogen and helium. This transition allowed photons to travel freely for the first time, resulting in a sudden increase in the universe's transparency. The flood of radiation. Once shimmering with a luminous opacity, the vastness of space has undergone a remarkable transformation, now allowing light to pass through with nearly unobstructed ease. This phenomenon is exemplified by our ability to capture the shadow cast by a black hole, an achievement that signifies one of the most extraordinary milestones in modern astronomy. In the year 2019, the global scientific community witnessed a groundbreaking moment when the pioneering efforts of the Event Horizon Telescope culminated in the release of the very first direct image of a black hole, or more precisely, of the shadow it cast against the glowing backdrop of its accretion disk. Although the black hole itself remains invisible, the radiant ring of superheated gas swirling precariously around the event horizon grants us a window into these cosmic enigmas. This particular black hole resides at the core of the galaxy known as M87, situated approximately 53 million light-years from Earth. The image unveiled a perfect circle, an unmistakable silhouette representing the domain from which no light can escape, encircled by a luminous halo, its shape and brightness twisted and distorted by the intense gravitational forces at play. It's important to understand that capturing such an image demanded not just sophisticated technology, but an extraordinary feat of international collaboration. Telescopes scattered across different continents coordinated seamlessly to function as a single, colossal lens capable of resolving the faint whispers of light from such a distant object. The achievement transcended the creation of a mere photograph. It stood as a silent triumph of scientific ingenuity and perseverance, offering humankind our first direct glimpse into some of the universe's most obscure and mysterious objects. What makes this feat even more profound is that we observe this phenomenon not through science fiction stories or theoretical models, but through beams of light traveling across unimaginable distances, revealing truths hidden within the fabric of space itself. Turning our gaze closer to home, we find that the vast universe presents us with a remarkable opportunity to observe a galaxy with nothing more than our naked eyes, without the aid of telescopes or special equipment. While most distant galaxies are so far removed that their light reaches us as faint, diffuse smudges, there exists one galaxy, visible to the unaided eye from nearly any dark, clear night sky, the Andromeda Galaxy. During tranquil, cloudless nights in the northern hemisphere, many sky watchers can spot its soft, hazy, oval-shaped glow, arching gracefully across the sky. Despite its apparent size and brightness, Andromeda is extraordinarily distant, lying about 2.5 million light-years away, meaning the light reaching our eyes began its voyage long before humans ever walked the Earth or developed civilization. Containing an estimated trillion stars, more than double the numbers found within the Milky Way, Andromeda is slowly, but inexorably, moving toward our own galaxy, a cosmic dance that spans millions of years. It is almost unfathomable to think that, standing under the open sky, one can observe the light from an entire galaxy, a colossal collection of stars, dust, and ancient remnants, something so vast, so old, that it has traveled across space for millions of years, waiting for the moment when it can be glimpsed by our eyes. All of this can be achieved without any technological aid, simply by looking upward into the dark, observing the faint glow of something truly ancient and expansive drifting silently through the cosmic void. In recent years, even the faintest echoes from the most distant corners of the universe have been detected thanks to highly sensitive instruments in space. In the year 2015, a tiny satellite named LIGO, an acronym for Laser Interferometer Gravitational Wave Observatory, captured something extraordinary, a subtle ripple propagating through the fabric of space-time itself. This faint disturbance, known as a gravitational wave, originated from a cataclysmic event over 1 billion light-years away, caused by the collision and merger of two black holes. As these titanic masses coalesced, they released energy in the form of gravitational waves that traveled through the universe at the speed of light, stretching and squeezing space-time in tiny, almost imperceptible ways. These distortions are so faint that they alter the dimensions of matter by less than the width of a proton, an unimaginably delicate measurement. Nevertheless, with incredibly precise and sensitive technology, scientists were able to detect these whispers from the cosmos, transforming the way we observe space and time. The success of LIGO and its counterparts was a testament to human ingenuity, confirming predictions made by the renowned physicist Albert Einstein more than a century earlier. Einstein theorized that massive cosmic events should generate ripples in space-time, but only with the advanced detectors of today could we ever hope to perceive these faint signals. Through this breakthrough, we have gained the ability to listen to the universe's deepest hums, transforming our understanding of phenomena that once lay beyond the reach of observation. The universe itself is in a state of perpetual expansion, a phenomenon that continues to accelerate over time. This ongoing stretching of space means that the distances between galaxies increase, with some galaxies receding from us at speeds. The absence of a particular celestial entity, such as a star or galaxy, is not necessarily felt in the immediate, everyday sense. Rather, it is the realization that its radiant light, which once reached our eyes and minds, can no longer travel across the vastness of space to reach us. Over the course of billions of years, a span so immense that it is difficult for the human mind to fully grasp, the observable universe will gradually diminish in size. This process is not merely about the universe expanding outward. It also subtly involves the universe fading away from our view. Essentially, The cosmic landscape is quietly letting go of its luminous parts, one by one, until only darkness and the unknown remain. Some black holes, intriguing in their origins and characteristics, might be primordial, born before the very stars that light up the night sky. While the majority of black holes emerge from the catastrophic collapse of massive stars, there exists an alternative possibility. These primordial black holes could have been formed in the earliest moments following the Big Bang, long before any stars or galaxies had even a chance to come into existence. Such black holes are theorized to originate from minute fluctuations in the ultra-dense, hot conditions that prevailed shortly after the universe's inception, regions where gravitational forces caused matter to coalesce into incredibly compact knots. Some of these primordial black holes might be infinitesimally small, comparable in size to a tiny asteroid or even less. Over cosmic time, however, others could have grown in mass, absorbing surrounding matter and merging with other black holes, thus increasing in size. Despite never having been directly observed, if these ancient entities do exist, they could provide vital clues to resolving some of the universe's greatest mysteries. They might help explain the elusive nature of dark matter, serve as seeds from which galaxies eventually formed, or offer new insights into the conditions of the universe's earliest moments. These black holes, predating stars and galaxies by unfathomable stretches of time, stand as silent, ancient fossils, remnants of the very seconds just after the universe's birth. In the grand and mysterious framework of the cosmos, particles that become entangled introduce an even more astonishing dimension. Quantum entanglement is considered one of the most bizarre and counterintuitive phenomena encountered in physics. When two particles are entangled, their properties, such as spin, position, or polarization, become fundamentally linked, regardless of the distance separating them. Altering one particle instantaneously influences the other, as if an invisible, unbreakable thread connects them across the universe. Although this phenomenon does not allow for faster-than-light communication, thus upholding the principles of relativity, it profoundly suggests that at the quantum level, reality is intertwined in ways that challenge our classical understanding. Some theoretical physicists speculate that entanglement might be woven into the very fabric of space-time itself, perhaps even playing a vital role in holding space and time together. If particles created during the early epochs of the universe remain entangled today, they could be stretched across the expanding cosmos, forming an unseen web of subtle quantum connections. These invisible threads might act as lingering echoes of the universe's infancy, quietly binding distant regions of space. In essence, quantum entanglement could serve as the cosmos's quiet memory, a network of subtle signals traversing the empty void between galaxies, a testament to the universe's deep, underlying interconnectedness that persists long after the initial formation. Turning now to the quantum nature of space itself, the vacuum of space is far from an empty void. Even in the most perfect vacuum, a place devoid of atoms, particles, or radiation, there remains an intrinsic form of energy. Quantum physics reveals that what we perceive as empty space is actually teeming with tiny, restless fluctuations. These fluctuations manifest as particles and antiparticles that momentarily appear, only to vanish again within incredibly short timescales. Fields that permeate space shift ever so slightly, never remaining completely still. And this ceaseless activity produces a form of energy known as vacuum energy. On cosmic scales, This energy is believed to influence the behavior of our universe in profound ways. In particular, it is thought to be connected to dark energy, the mysterious force responsible for accelerating the universe's expansion. Unlike conventional forms of energy that dilute as the universe expands, vacuum energy remains constant, exerting a persistent pressure that stretches space at an ever-increasing rate. Paradoxically, this means that the more empty space there is, the more energy it appears to contain, amplifying the universe's expansion. This strange quality, that an absence or nothingness can generate something, captures the imagination and underscores the enigmatic nature of the cosmos. It is as though the fundamental fabric of empty space itself holds the potential to propel the universe apart, pushing its galaxies steadily farther from each other. Finally, black holes, almost mythic in their nature, continue to fascinate scientists and the public alike. Traditionally considered the ultimate darkness, black holes are so dense that nothing, not even light, can escape their immense gravitational pull once it crosses a boundary known as the event. At the very boundary, where the intense pull of a black hole's event horizon begins to dominate, strange phenomena occur that challenge our understanding of physics and the fabric of space-time itself. It is here, in this mysterious and almost incomprehensible zone, that quantum mechanics and general relativity intersect in a delicate yet profoundly significant way. Occasionally, tiny pairs of virtual particles, which normally pop into existence out of the vacuum for fleeting moments, can become a little more than just fleeting ideas. In some instances, one particle from this pair manages to gain enough energy to escape this near-immense gravitational grip, leaving its partner behind to fall inward. This escaped particle transitions from a virtual state to a real, measurable particle, effectively carrying away a minuscule amount of energy from the black hole. This process, known as Hawking radiation, implies that black holes are not entirely eternal islands of darkness, but gradually lose mass as this trickle of energy escapes into space. Over unimaginably long stretches of cosmic time, far beyond human comprehension, this continuous, almost imperceptible leakage can cause a black hole to gradually diminish in size. Given enough billions or even trillions of years, a span exceeding the current age of the universe, this slow process can lead to the complete evaporation and disappearance of the black hole. It is a silent, subtle kind of ending, lacking any explosive finale or catastrophic event. Instead, it is a slow fade into nothingness, an almost gentle withdrawal of the black hole's presence from the universe. Moving away from the enigmatic depths of black holes, we find that the universe's most prevalent form of matter is unlike the solid, liquid, or gaseous states we're familiar with on Earth. In truth, the dominant form throughout the cosmos is something called plasma, an extraordinary state of matter that defies everyday intuition. Unlike solids or liquids, plasma is an ionized gas composed of a dense collection of charged particles, where electrons and atomic nuclei move freely and independently. It is this freedom of movement and high energy state that give plasma its unique properties. We observe plasma in the fiery glow of stars, where nuclear fusion powers their brilliance, as well as in the solar wind, a continuous stream of charged particles emanating from our sun and spreading through the solar system. It is also found in the vast stretches of the interstellar medium, the space lying between stars, and in the colossal regions that separate galaxies from one another. Essentially, The vast majority of visible matter in the universe exists in this highly energized, glowing plasma state. Due to its charged nature, plasma behaves in ways that are quite different from solids, liquids, or gases. It responds actively to magnetic fields, which can shape, twist, and control its movement. It flows smoothly, like a fluid, but can also generate powerful electrical currents that travel across enormous distances, creating dazzling auroras and other celestial phenomena. On Earth, our encounters with plasma are limited mostly to brief, spectacular displays like lightning bolts illuminating the sky during thunderstorms, the fiery glow of a bonfire, or the vibrant auras of neon lights. Yet, in the vastness of space, plasma is ubiquitous, shaping the universe's luminous tapestry, constantly flowing, glowing, and influencing the structure and evolution of cosmic environments beyond our immediate perception. Furthermore, gravity, the force that governs the motion of planets, stars, and galaxies, behaves in ways that are far more subtle and profound than simple attraction. When massive, dense objects, such as black holes or neutron stars, collide and merge or undergo dramatic events, they generate ripples in the very fabric of space-time, known as gravitational waves. Similar to ripples spreading across a still pond after a stone is thrown in, these waves travel outward in all directions, stretching and squeezing space itself as they go. Gravity does not merely pull objects toward each other, but can ripple through space-time, propagating faster than anything else in the universe, traveling at the speed of light, the ultimate speed limit. It took many decades of scientific effort and technological innovation to develop detectors sensitive enough to perceive these faint, elusive disturbances. Now, thanks to advanced observatories and highly refined instruments, we are able to listen to these cosmic whispers from our planet. Each gravitational wave carries within it rich information about cataclysmic events that occurred far across the universe, about the immense mass involved in mergers, the rapid spin of the merging bodies, and the degree of warp such events induce in the fabric of space-time. While these waves are inaudible to human ears, they are real, measurable phenomena, subtle, but with the power to reveal the most violent and mysterious processes in the universe, acting as gentle, almost delicate, probes into the cosmos's deepest secrets. Alongside this, the universe reveals a breathtakingly complex, interconnected structure known as the cosmic web. When astronomers map the vast distribution of galaxies across the universe, they discover an intricate network resembling a vast tapestry woven from countless threads. On the largest scales, matter seems organized into filaments, clusters, and voids, a vast cosmic web that connects everything in the James Webb Space Telescope possesses a remarkable ability to observe galaxies that no longer exist in their original form, a phenomenon that highlights the extraordinary nature of modern astronomy. This sophisticated instrument was meticulously designed to peer deeper into the universe than any previous telescope had ever managed, and in doing so, it also enables us to look further back in time. The reason for this remarkable capability lies in the fundamental physics of light. Because light takes a finite amount of time to traverse the cosmic expanses, the galaxies we observe are seen as they were billions of years ago, long before the present moment. Some of the distant galaxies captured in Webb's view may have undergone dramatic transformations, or even ceased to exist altogether since their light set out on its journey toward us. Over the vast epochs of cosmic history, these galaxies could have merged with others, faded away into obscurity, or changed so completely that they no longer resemble their original forms. Despite these changes, the light from these distant worlds continues to arrive at the telescope, serving as an unaltered snapshot frozen in the fabric of space and time, reminding us that the universe's history is vividly inscribed in the light that reaches us. This phenomenon encapsulates one of the more subtle, yet profound, mysteries of astronomy. Telescopes do not provide us with a real-time view of what exists out there now. Instead, they deliver images that are, in essence, visual records of the past. Any image taken from a deep field, an image capturing some of the most distant galaxies, is akin to a time machine, offering a glimpse into worlds that existed billions of years before our own planet was formed. These images are galleries of vanished light, spectacular, ancient flickers from galaxies that once shone brightly in the distant cosmos. The light reaching us from these galaxies was emitted before Earth had even come into being, before the sun's ignition, and long before the formation of the solar system. When astronomers observe a galaxy billions of light years away, they are not merely measuring the galaxy's distance in space. They are also measuring its age. The light from such a galaxy began its long journey through the expanding universe long before Earth existed. In some cases, the light we detect today left its source over 10 billion years ago. This ancient glow has traversed the ever-expanding cosmic void, stretched and redshifted along the way, until it finally reached the sensitive optics of our telescopes. Through this process, we are essentially witnessing the universe's distant past unfold in real time, as if watching a cosmic historical record. The stars you might see in those distant galaxies are likely long gone, their light serving as gentle reminders that the night sky holds stories older than the Earth itself. Furthermore, entire galaxies are not immune to obscuration. They can vanish from view behind thick veils of interstellar dust clouds, which act as cosmic curtains, sometimes hiding these worlds entirely from optical sight. Even the enormous scale of a galaxy can be concealed behind these dusty shrouds. In certain regions of space, massive concentrations of dust, composed of tiny grains of carbon, silicates, and other microscopic particles, drift through cold molecular clouds. These clouds are dense and cold, acting as cosmic smokescreens that intercept and absorb much of the visible light emanating from objects behind them. When a galaxy is hidden behind such dust clouds, it appears faint or entirely invisible to telescopes operating in the visible spectrum. Only by employing specialized investigative tools that observe in infrared, radio, or X-ray wavelengths can astronomers sometimes pierce through the dust clouds and detect these galaxies. Infrared and radio photons are less prone to scattering by dust, allowing the concealed galaxies to reveal their presence. Over the years, astronomers have uncovered entire populations of galaxies lurking behind what once appeared to be clear patches of sky, demonstrating that apparent darkness or emptiness often masks rich and complex structures. This reveals a vital truth. In space, darkness does not always equate to emptiness or absence. Sometimes it indicates regions waiting to be revealed under the right observational conditions. In the realm of cosmic optics, another fascinating phenomenon emerges in the form of gravitational lensing, where the far-reaching influence of gravity can distort and magnify the light from distant objects. In certain cases, a galaxy can be surrounded by perfectly circular arcs of lensed light, creating something known as Einstein rings. These magnificent structures occur when the gravity of a massive foreground galaxy acts as a lens, bending the light from even more distant objects positioned along the same line of sight. When the alignment between the observer, the lensing galaxy, and the distant source is precise, the displaced light forms a seamless glowing ring, a true spectacle of nature. Such Einstein rings are rare, yet visually stunning, astrophysical spectacles that embody the combined effects of gravity and perspective. They are not the result of motion or celestial dance, but are instead the outcome of the warping space around massive objects. The light that creates these rings can originate from various distant sources: another galaxy, a quasar, or even a supernova. These luminous rings play a crucial role in modern astronomy, serving as sophisticated tools that enable scientists to determine the mass of entire galaxies, create detailed maps of elusive dark matter, and peer back into the conditions of the early universe. These rings are silent witnesses to cosmic phenomena, perfect, almost surreal illusions that emerge naturally from the fabric of space itself. They act as cosmic lenses, bending light in a manner dictated purely by the shape and curvature of space-time. Phenomena that can be visualized as a natural, invisible magnifying glass, offering a glimpse of the universe in exquisite detail. The concept of the universe extends far beyond what we can immediately comprehend. It might be infinite in scope. When we gaze upward, admiring the twinkling stars, it's instinctive for us to wonder whether somewhere out there, beyond what we can see, an ultimate boundary exists, an edge that marks the end of everything. However, current astronomical observations increasingly suggest that this is unlikely. Instead, the universe appears to stretch out endlessly, with no definitive boundary, no singular dividing line. What we can observe, the observable universe, is merely a finite portion of an otherwise boundless expanse. But what lies beyond that corner of the cosmos remains speculative. It might go on forever, extending into an infinite horizon of space. In this vast reality, there is no center and no boundary, just sprawling galaxies, countless stars, and endless stretches of emptiness that seem to fade gently into the unknown. If this notion holds true, then the majority of the universe will always be beyond the reach of our instruments and understanding. No matter how powerful our telescopes become, or how long we wait in hope, we will never be able to witness the entire universe in its entirety. An infinite universe doesn't necessarily offer infinite opportunities or possibilities, but it does embody endlessness, a tranquil, expansive void that stretches out without end, evoking a sense of quiet majesty and infinite succession. Cosmic rays, high-energy particles originating from deep space, continually bombard our planet, striking the Earth every single second, an unceasing din of energetic messengers. These particles are diverse. Some emerge from our Sun, while others originate from distant galaxies or even more remote cosmic regions. They are primarily composed of protons, atomic nuclei, and fragments of atoms, all accelerated to extraordinary velocities by violent astrophysical events such as supernova explosions, the intense gravitational pull of black holes, or possibly other mysterious forces scattered across the universe. Earth's magnetic field acts as a shield, deflecting many of these energetic particles, and our atmosphere absorbs most of them, rendering them harmless. Yet, a small fraction manages to reach the surface, and an even smaller number can pass directly through living tissue, passing through you and me without causing harm. Although these particles pose little danger in small doses, they serve as a constant, invisible reminder that space is anything but empty. Instead, it is a dynamic realm, teeming with motion, energy, and countless invisible signals, messages from distant, often ancient cosmic events. When a cosmic ray finally strikes a detector or instrument, it carries with it a story that began light years away, a narrative that might trace back to a supernova explosion, a black hole's voracious feeding frenzy, or some other extraordinary phenomenon occurring eons ago, far beyond our reach. The notion of a before the Big Bang is a puzzling and complex concept, and it challenges our traditional understanding of time and existence. While the phrase before the Big Bang may seem intuitive or natural, it may be fundamentally nonsensical within the framework of modern physics. According to Einstein's theory of general relativity, and supported by many cosmological models, time itself may have originated at the moment of the Big Bang. In other words, the Big Bang was not merely the inception of matter and energy, but also the beginning of space and time, an event that marks the absolute origin point. Asking what existed or occurred before that moment is akin to questioning what is north of the North Pole, an inquiry that loses meaning because the concept of before presupposes the existence of time itself, which did not exist prior to the event. Some theories propose the existence of a previous state or an entirely different universe that preceded ours, while others suggest a quantum realm where the normal rules of cause and effect break down, or even where time itself behaves in an unfamiliar way or might not exist at all. Nevertheless, in most reputable models, the notion of a before the Big Bang is purely speculative. It is not a place we can visit, nor a concept we can meaningfully imagine, much like trying to peer into a dark, unlit abyss with a flashlight that illuminates nothing beyond the event horizon. It's important to understand that the Big Bang was not an explosion that happened somewhere within pre-existing space. Rather, it was the very point at which space and time themselves came into existence, an event so fundamental that any notion of a universe before that moment is physically and philosophically problematic. The discovery, the earliest quasars observed in our universe were so distant that the light reaching us from them had traveled for billions of years across the vast expanse of space before finally arriving in our telescopes. Despite the incredible distance, these quasars appeared as tiny points of light, almost indistinguishable from distant stars at first glance. This was a classic case of misidentification, initially leading scientists to think they were ordinary stars. Yet, this mistaken impression turned out to be one of the most groundbreaking discoveries in the field of astronomy, revealing objects of extraordinary brightness, far beyond anything previously observed. The realization opened up new avenues of understanding the early universe and its evolution, transforming our perspective on cosmic history. Meanwhile, our immediate cosmic neighborhood, known as the local group of galaxies, is gradually moving in a specific direction, driven by unseen gravitational forces. The Milky Way galaxy, our home, is far from being a static entity. It, along with the neighboring Andromeda galaxy and dozens of smaller satellite galaxies, drifts through the cosmos as part of a loosely bound collection often referred to as the local group. But this entire assembly isn't simply drifting aimlessly. It is in motion toward a larger region of space that exerts a powerful gravitational pull. This zone is known as the Great Attractor, a mysterious and massive gravitational anomaly that pulls the local group. and ultimately our galaxy towards it. Beyond the influence of the Great Attractor, there exists an even more enigmatic region, the Shapley supercluster, and possibly other superclusters yet to be fully mapped or understood. These colossal clusters are concealed behind curtains of dense interstellar matter, obscuring our view of their true nature. Nevertheless, the effects of their gravity can be detected through their influence on galaxy motions, allowing astronomers to infer their presence even if they remain largely hidden from direct observation. It is as though our cosmic neighborhood is gradually slipping, and indeed gliding, towards something enormous, a shadowy behemoth whose full extent remains concealed. We only know that we are moving in that direction, and that the unseen giants of gravity are pulling us forward, guiding us through the darkness. At present, we find ourselves experiencing what could be dubbed the universe's stellar springtime. Currently, the cosmos teems with countless stars that are burning brightly, forming anew, and occasionally exploding in spectacular supernovae. This vibrant phase of cosmic activity, however, is a relatively recent chapter in the universe's long history. In the initial hundreds of millions of years following the Big Bang, no stars existed at all. During that primordial period, the universe was a dark, featureless expanse. It wasn't until some of the first hydrogen and helium gas clouds cooled sufficiently and collapsed under gravity that the earliest stars ignited, illuminating their surroundings and kickstarting the ongoing process of cosmic evolution. Since then, the rate of star formation has varied, rising, reaching a peak, and then gradually declining as conditions changed. Today, we inhabit what might be called a cosmic spring, a time when the universe continues to birth new stars, but at a diminishing rate compared to its earlier epochs. This period represents a balance, a moment of respite before the eventual decline. In the distant future, the last stars in the universe will ignite, lighting the cosmic darkness for what might be the final time. After that, the universe will begin a slow, inevitable fading into darkness as star formation ceases altogether. The universe's glow will diminish gradually, without sudden violence or catastrophic change, fading to blackness through an almost imperceptible decline. This eventual darkness will not be marked by a sudden end, but by a slow, quiet dimming. What remains will be a universe filled with remnants, black holes, the collapsed cores of massive stars, white dwarfs, the cooled remnants of once bright stars like our own sun, neutron stars, extraordinarily dense remains left after supernova explosions, and vast stretches of emptiness where no significant light or activity persists. Over unimaginably long timescales, even the slow-burning red dwarfs, stars capable of shining for trillions of years, will eventually exhaust their fuel, cooling into inert embers. The universe will then be a cold, silent expanse, where matter exists in a state of profound tranquility and stillness, awaiting a fate that is not tragic, but simply the natural end of cosmic evolution. Most of the stars and matter in the universe are, in fact, invisible to us. When we gaze into the night sky, we see only a small, luminous fraction of what actually fills the cosmos. Stars, galaxies, nebulae, the glowing clouds of gas and dust represent merely the visible tip of an enormous, mostly hidden universe. The majority of matter does not emit, reflect, or scatter light. It remains invisible, lurking unseen. This mysterious, invisible substance, known as dark matter, constitutes a significant portion of the universe's total mass. Although scientists have yet to directly detect dark matter, they are confident of its existence owing to its gravitational effects. For instance, light from distant celestial objects behaves in a way that often defies our initial expectations and straightforward understanding. When astronomers observe galaxies or other remote bodies, they notice that the light reaching us has been bent or distorted more than simple models would predict. This discrepancy points to the presence of an extraordinary kind of matter that, although invisible, exerts a substantial gravitational influence on the universe's structure. Clusters of galaxies tend to cling together with an internal cohesion far stronger than their visible mass could provide. These observations strongly imply that there exists an extensive quantity of unseen matter, which astronomers have aptly named dark matter. Its total amount appears to be at least 5 times greater than all the ordinary observable matter, like stars, planets, and gas, that we can see with our telescopes. This mysterious substance, forming an almost invisible framework, pervades the entire universe, orchestrating the cosmic web that holds galaxies, galaxy clusters, and other large-scale structures in their rightful places. Despite its omnipresence, dark matter eludes direct detection, as it does not emit, reflect, or absorb light in any way that we can currently measure. It's akin to an unseen scaffolding, silently maintaining the universe's architecture, holding galaxies together in their grand cosmic dance. Simultaneously, the light from the earliest galaxies has undergone a fascinating transformation known as cosmic redshift. As this ancient light travels across the vast expanse of space, it doesn't merely propagate outward. It stretches and elongates because of the ongoing expansion of the universe itself. The expansion acts like an invisible hand, pulling the fabric of space apart, and, in doing so, stretching the wavelengths of the light traveling through it. Light emitted billions of years ago by the first galaxies originally appeared as visible radiation, what our eyes can see. But now, as it journeys through the ever-expanding cosmos, these waves have been stretched into longer, redder wavelengths, a phenomenon called redshift. This shift is a crucial tool for astronomers. By measuring how much the light has been stretched, they can determine how far away, and, consequently, how old the source galaxy is. Essentially, the greater the redshift, the farther back in time we are observing. Thanks to sophisticated telescopes like the James Webb Space Telescope, astronomers are increasingly able to capture and analyze this ancient, stretched light. What once was fiery, bright emission from primordial stars now arrives at Earth as a faint, crimson whisper, a remnant of the universe's infancy, softened and reddened after billions of years of being carried along by cosmic expansion. A provocative idea that has been gaining attention among some physicists is the notion that our universe may fundamentally resemble a hologram. Although this concept sounds more like science fiction than science fact, it is a hypothesis grounded in serious theoretical exploration. The holographic principle suggests that our familiar three-dimensional universe might, in fact, be a projection, a kind of illusion emerging from a deeper, two-dimensional reality. This idea is inspired largely by the perplexing behavior of black holes. When scientists examine black holes, they find that all the information describing what falls into them appears to be encoded on their surfaces, rather than deep within their volumes. It's as if the entire content of a black hole is stored on an outer shell, challenging traditional notions of how information and space itself work. Some theories extend this concept further, proposing that the entire universe could operate under similar principles. What we perceive as three-dimensional space, with its depths and distances, might simply be a kind of profound illusion, a math-driven projection of information stored on a distant boundary. While these ideas remain unproven and unlikely to change our everyday experiences, they serve as a compelling reminder that reality, even at its most tangible and seemingly solid, might not be as concrete as we traditionally think. Our universe may be formed by fundamentally different rules than those of our everyday intuition. On the smallest scales, space itself might not be the uniform, continuous fabric it appears to be. To the naked eye, and even under the most powerful microscopes, space looks smooth and endless. It seems to extend infinitely without interruption, and on microscopic levels, it remains featureless and continuous, still in essence. However, some of the most advanced theories of quantum gravity propose a radically different picture. That space is composed of minuscule, discrete building blocks, similar to the pixels in a digital image or grains of sand. The smallest meaningful measurement in this context is called the Planck length, approximately 10 raised to the power of negative 35 meters, a scale so tiny that it defies direct observation with current technology. At this fundamental level, the smoothness we observe breaks down into a granular structure, creating a kind of foamy, grainy texture at the very heart of space and time itself. Although we lack the means to verify this directly at the moment, if this theory holds true, it implies that all phenomena, stars, galaxies, thoughts, even the experience of sleep, do not occur in a perfect void, but within a universe that has an intrinsic, granular. The universe is home to some of the most extraordinary cosmic phenomena, among which are the stellar remnants known as neutron stars. These compact objects are essentially the collapsed cores of massive stars that have undergone supernova explosions. When a star that was many times more massive than our Sun exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The result is an incredibly dense sphere composed primarily of neutrons, with a radius measuring only about 12 miles, roughly the size of a small city, yet containing more mass than our Sun. One of the most captivating features of neutron stars is their astonishing rotation rates. Some spin at hundreds of times per second, their cores turning faster than the blades of a household blender. Imagine a city-sized sphere of densely packed nuclear matter spinning so rapidly that if it were not so tightly bound by gravity, it would fly apart. These objects are sometimes called pulsars because they emit beams of electromagnetic radiation from their magnetic poles. As they rotate, these beams sweep across space with unwavering precision, much like cosmic lighthouses blink their signals across the night sky. To an observer on Earth, these beams appear as regular pulses of light or radio waves, ticking away with extraordinary regularity, serving as some of the universe's most precise natural clocks. Many of these neutron stars are found in close orbit around companion stars, some in tight, gravitationally bound couples. These binary systems often lead to dramatic phenomena. As the neutron star pulls in matter from its neighboring star, it accelerates even further, spinning faster and emitting intense radiation. The gravitational influence of these companions can cause the neutron star to gain sudden bursts of energy, making it one of the fastest and most precise rotators in existence. In effect, these pulsars are some of the universe's most ancient timekeepers, quietly measuring cosmic time with astonishing reliability amid the darkness. Looking beyond these remarkable revolutions of stellar remnants, cosmologists have long pondered the ultimate destiny of the universe itself. In the distant past, some believed that the universe might eventually undergo a catastrophic collapse, known as the Big Crunch, where expansion halts and reverse, pulling everything back into an infinitely dense point. However, recent evidence suggests an entirely different fate awaits the cosmos, one characterized by a slow, ceaseless expansion that persists indefinitely. As the universe continues to stretch outward, galaxies drift farther apart, diminishing in their apparent brightness and density. Star formation rates decline gradually as the raw materials, gas and dust, become increasingly scarce. Over vast stretches of time, the luminous night sky will grow progressively darker, the twinkling of stars gradually fading away. The individual stars within galaxies will burn out, one by one, until only their remnants remain. Black holes, the incredibly dense and gravitationally powerful entities that once devoured matter eagerly, will eventually evaporate through a slow process called Hawking radiation, a phenomenon that predicts black holes can slowly lose energy over enormous timescales. Meanwhile, even the fundamental particles that make up matter might begin to decay or become indistinguishable in their energy states, leading the universe into a state of profound silence and emptiness. This long, gentle fade, often called heat death, is not marked by a sudden event or catastrophic explosion, but unfolds as an unhurried fading into darkness. Over trillions upon trillions of years, a timescale so vast that human comprehension can scarcely grasp, the universe will become increasingly inert. All matter, energy, and the very fabric of structure will diffuse into an immense, cold void. It is a quiet, almost peaceful ending, neither fiery nor icy, but characterized by a pervasive stillness. In this final state, the universe's initial act of creation, its cosmic whisper, will be gently silenced as it gradually dissolves into a limitless, silent expanse. Turning our gaze inward, some galaxies display extraordinary phenomena known as superwinds. These colossal outflows of matter are particularly prevalent at the centers of galaxies that host active black holes or regions rife with intense star formation. These superwinds are powerful and far-reaching, capable of extending tens of thousands of light years into the surrounding intergalactic space. They originate from the combined effects of high-energy radiation, magnetic fields, and the explosive energy released by supernovae, cataclysmic explosions marking the deaths of massive stars. As the winds blow outward, they carry vast quantities of gas, dust, and even newly formed stars away from the galactic core. This process of galactic shedding over cosmic timescales can have profound implications for the evolution of galaxies. By removing essential star-forming material, these superwinds often render galaxies quiescent and red, a peaceful but dormant state. Conversely, they serve a vital cosmic role by dispersing heavy elements, metals formed in the cores of stars, into the larger cosmic web, enriching the intergalactic medium. These elements act as building blocks for future generations of stars and planets, seeding the galaxy with the raw materials necessary for complex chemistry and life. In essence, a galaxy can be seen as some scientists and astronomers propose the intriguing idea that we might currently be dwelling within one of these vast, empty regions known as cosmic voids. These voids are enormous expanses of space that contain significantly fewer galaxies stars, and matter than the average density observed across the universe. In fact, their density is lower than what we typically expect when considering the cosmic background radiation and the distribution of matter on large scales. If this hypothesis holds true, it could provide crucial insights into some of the perplexing observations that astronomers have encountered over recent years. For instance, it might help us better understand why the universe appears to be expanding at a certain rate, or why particular patterns emerge in the cosmic microwave background, the faint afterglow of the Big Bang that fills the universe. Though living within a void might not noticeably alter our daily routines or the way we go about our lives, this perspective shifts our understanding of what we perceive as emptiness. What seems like an empty patch of space could, in fact, be part of an immense structure, a silent, central region of a gigantic cosmic bubble, gently adrift in a vast web woven from invisible gravitational forces. It's as if we are floating through a quiet, expansive foam of cosmic fabric within a universe far more complex and interconnected than it initially appears. Turning our focus to some of the universe's most extraordinary celestial objects, we find magnetars, neutron stars with magnetic fields so unimaginably strong that they surpass Earth's magnetic field by trillions of times. A neutron star itself is already an incredibly dense remnant left after a massive star exhausts its fuel and collapses under its own gravity. These remnants are often roughly the size of a city, but contain more mass than our Sun, squeezed into an incredibly compact space. Among these, magnetars are distinguished by their extreme magnetic environments. While Earth's magnetic field is just sufficient to guide a compass, a magnetar's magnetic field is so intense that it could erase data from thousands of miles away, cause significant distortions in atomic structures, or even tear matter apart altogether. These incredibly powerful magnetic fields are not permanent. They gradually decay over time. Nonetheless, during their active periods, magnetars produce spectacular flares and bursts of high-energy radiation that can be detected across the vastness of space. In fact, a single burst from a magnetar, even one located many millions of light years away, is strong enough to be observed from Earth. Such phenomena are beyond the capabilities of any laboratory here on our planet to recreate, positioning magnetars among the universe's most extreme and awe-inspiring objects. They appear as silent giants cloaked in invisible forces, remnants of star explosions, their existence a testament to the universe's capacity for creation and destruction. They are the very essence of cosmic extremes, dense as a city, quiet as the void, yet wielding forces of such magnitude that they challenge our understanding of physics. Moving even further out into the depths of space, we encounter some of the universe's largest known structures, such as vast quasar groups. Quasars are the luminous, energetic cores of distant active galaxies, powered by supermassive black holes amid swirling disks of matter. In 2013, astronomers unveiled a colossal structure composed of these energetic objects, an immense arrangement spanning over 4 billion light-years across. This impressive formation, called a large quasar group, stretches across such an enormous volume that it raises fundamental questions about the uniformity and large-scale structure of the cosmos. According to the prevailing theories in cosmology, on the grandest scales, the universe should appear relatively smooth and homogeneous, with no structures exceeding certain size limits. However, this quasar group defies those expectations, being larger than the theoretical maximum size predicted by current models. It is composed of dozens of quasars, interconnected across an enormous cosmic distance, hinting that in the early universe, larger and more complex patterns of matter might have formed than previously believed. There remains some debate among scientists as to whether this structure is an actual physical entity, an interconnected entity in the fabric of space, or simply a statistical anomaly, a fluke of probability. Regardless of its true nature, this discovery underscores the fact that the universe's architecture is more intricate and interconnected than our existing models suggest. It reminds us that the cosmos may harbor vast, complex networks or structures that challenge our understanding and prompt us to rethink the fundamental principles guiding cosmic evolution. Finally, delving into the mysterious realm of black holes, we find objects capable of bending space itself into a funnel of time. A black hole does not simply act as a gravitational trap that captures light. Rather, it warps the very fabric of spacetime. As an object approaches a black hole's event horizon, the boundary beyond which nothing can escape, the geometry of space begins to bend inward, and time itself appears to slow down dramatically. To an outside observer, watching from afar, time near the event horizon seems to crawl to a near standstill. At the very brink of the black hole, this process slows so much that, effectively, it almost stops. This, because the universe is continually expanding at an accelerating pace, certain regions within it are already receding from us at speeds faster than that of light. This is not just a theoretical curiosity, but a fundamental consequence of cosmic expansion, which has profound implications for what we can observe and communicate across the cosmos. In practical terms, this means that no matter how long we wait or how advanced our technology becomes, the light emitted from these distant regions, those parts of the universe moving away so quickly, will never be able to reach us. The universe has created a kind of cosmic horizon, beyond which information cannot travel back to us due to the relentless stretching of space itself. Conversely, the same principle applies in the opposite direction. Certain locations are forever inaccessible because the space lying in between is expanding too rapidly, effectively tearing apart any potential signals or messages we might attempt to send. As the universe continues its expansion over unimaginably long timescales, more and more regions will slip beyond our observational reach, becoming isolated islands lost in the vast darkness of space. Eventually, each galaxy will be surrounded by a dark, silent void, cut off from the rest of the universe, akin to an ancient, solitary lighthouse that no longer illuminates for others. This process does not violate the fundamental laws of physics. Nothing is exceeding the universal speed limit of light by moving through space. Instead, it is the very fabric of space itself that is expanding calmly and relentlessly, creating a cosmic separation that becomes insurmountable in the infinite future. In this way, the universe's growth acts as a cosmic barrier, forever partitioning regions from one another and shaping a universe where isolation is inevitable on grand scales. When considering the origins of elements, it's fascinating to note that the heaviest of them all, gold, can only be forged under the most extreme and extraordinary conditions. The process of creating such dense, luminous atoms does not occur in the cores of typical stars like our Sun, where lighter elements are produced through nuclear fusion. Instead, gold, along with other heavy elements like platinum and uranium, is born from cataclysmic cosmic events. violent collisions between neutron stars, or specific types of supernova explosions. During these violent encounters, the enormous energy, heat, and pressure generated are so intense that atomic nuclei are smashed together at velocities close to the speed of light, enabling the formation of heavy nuclei. These rare and precious atoms are then expelled into surrounding space, dispersing across vast clouds of gas and dust, eventually becoming incorporated into new stars, planets, and even the building blocks of life itself. Remarkably, every piece of gold, be it a luxurious ring or a sparkling fleck of dust, originated from such a cosmic disaster, a violent event that took place long before our planet even formed. In this sense, gold is more than just a beautiful, valuable element. It's an ancient relic, a stellar remnant that embodies the universe's capacity for forge and creation amidst chaos. It carries with it the story of violent stellar explosions and cosmic upheavals, a silent testimony from an era when the universe was in the throes of forging its most precious treasures in the intense fires of stellar death. As our view extends across the universe, the expanding space between galaxies influences the very nature of the light that reaches us. Light from distant galaxies is not just a snapshot of the past. It bears the marks of the vast, stretching fabric through which it has traveled. When we gaze into the depths of space and observe the faint glow from remote galaxies, what we see is not only an image from long ago, but also a light wave that has been stretched and altered during its journey across the expanding universe. As the universe expands, the distance the light must traverse increases, and simultaneously, the light itself becomes stretched out, causing its wavelength to lengthen. This phenomenon, known as cosmological redshift, results in the light shifting toward the red part of the spectrum. Crucially, this does not mean that the light is slowing down or losing energy through any collision or absorption. It merely indicates that the space through which it travels has grown larger, stretching the wave's length. It's akin to a stretching rubber band. As it expands, its vibrations become longer and more stretched out. The universe effectively elongates the signal as it makes its way to us, a silent and persistent stretching that encodes the universe's ongoing expansion. When astronomers analyze distant galaxies, they are not merely measuring their age or how far away they are. They are also observing how much the universe has expanded since that light was emitted, capturing an almost poetic record of the universe's steady, breath-like expansion. In this way, the distant light acts as a cosmic messenger, silently carrying information about the universe's history, stretching across time and space in a process that reveals the universe's unending growth. The universe also holds a remarkable record of its earliest moments, a record that manifests as primordial sound waves imprinted into its very structure. These waves originated long before atoms could form. At a time when matter and energy were tightly, imagine a vast, ceaseless wave that never truly diminishes in strength, gently yet persistently sculpting the very fabric of the universe. This undetectable force weaves through the cosmos, influencing structures on an incomprehensibly grand scale. Galaxies, massive assemblies of countless stars, gas, and dark matter, can be gradually and invisibly consumed by even larger galaxies. Such colossal entities can engulf their smaller counterparts completely, leaving behind no obvious sign of their merger. Over cosmic timescales, stretching billions or even trillions of years, these interactions are far from violent confrontations. Rather, They unfold with graceful subtlety, almost delicately, as if the universe itself is engaging in a slow dance of absorption and transformation. When a diminutive galaxy ventures too close to a more immense one, the dominant galaxy's gravitational tides can tear it apart, pulling stars away into elongated tidal streams that stretch across the sky like celestial ribbons. These stellar remnants are then assimilated into the grand halo surrounding the larger galaxy, gradually blending and dispersing until the original smaller galaxy ceases to be distinguishable from its surroundings. Scientists have found ample evidence of such ancient mergers around our own home galaxy, the Milky Way, where long, shimmering streams of stars zigzag across the night sky, silent witnesses to once separate galaxies now merged into the cosmic mosaic. This slow, graceful process has earned the name galactic cannibalism, emphasizing its nature as a form of cosmic digestion rather than outright violence. Yet, despite its perceived gentleness, this mechanism is an unceasing, inevitable aspect of galactic evolution. Over eons, giant galaxies continually grow, not by the dramatic birth of new stars or smashing together in furious collisions, but through this quiet, persistent consumption of smaller companions. It is a process characterized by gentle absorption, where each galactic merger leaves only faint ripples, subtle fingerprints, etched into the distribution of stars and dark matter. Among these stars, some flicker with an unsteady light, reminiscent of tiny fireflies dancing across the dark night. Not all stars burn with a steady brightness. Many exhibit pulsations, variations in shimmer, or dimming and brightening that follow rhythmic patterns. These are known as variable stars, and their changing luminosity arises from a variety of internal and external causes. Some pulsate due to pressure waves moving within their interiors. Others undergo surface eruptions or are periodically eclipsed by invisible companions orbiting nearby. From our vantage point on Earth, they appear as gentle, rhythmic blinking in the vast celestial tapestry, flashing with a slow, predictable beat that can be likened to a cosmic heartbeat. The period of their variations ranges widely. Some complete their entire cycle within just a few hours, while others take several years to recur. Remarkably, these variations are not random, but often follow precise, nearly identical patterns over extended periods. Such consistency turns variable stars into invaluable tools for astronomers, who utilize them as natural celestial clocks. By meticulously observing their flickering, astronomers can determine how far away these stars are, as well as their true intrinsic brightness. This method has become fundamental in measuring distances across immense cosmic expanses, allowing us to chart the universe with impressive accuracy. Stars, however, do more than just burn steadily. Some breathe. Their brightness fluctuates in ways that hint at complex internal processes. Meanwhile, black holes, those mysterious regions of space-time where gravity is so intense that nothing, not even light, can escape, do not always reside peacefully at galaxy centers. Some black holes are wanderers, roaming through space independently of any particular galaxy. These rogue black holes can be ejected from their birthplaces during gravitational interactions, expelled from their host galaxy in the chaos of celestial collisions, or propelled away by the recoil effect that occurs during black hole mergers. Once freed, they drift silently through the dark void of interstellar space, their presence remaining hidden unless they encounter gas or stars nearby. Such encounters can cause them to emit faint signals, but generally, these wandering black holes are nearly impossible to detect, hidden in the shadows of darkness. These lone black holes carry no fixed orbit, no companion star, and no permanent residence. What they possess is a mass so extreme that it continues to pull inward relentlessly, an unending fall inward fueled by gravity's deep and unrelenting grip. Even black holes are not immune to the dramatic effects of cosmic collisions. When two black holes collide and merge, a cataclysmic event, they emit a burst of gravitational waves, ripples in spacetime that travel outward at the speed of light. If the merger is asymmetrical, if more energy is released in one direction, the newly formed black hole can be given a kick, a recoil velocity that can hurl it away from its original position at thousands of kilometers per second. Incredibly, such recoil velocities can be so immense that the black hole is flung entirely out of its host galaxy, destined to drift through the vast emptiness of intergalactic space, lost forever in even the most colossal and seemingly immovable objects in the universe. Those that appear to be firmly anchored and unchangeable can be shifted, shaped, or influenced by a particular kind of wave. These waves are not like the daily waves lapping shores, but are instead cosmic ripples that possess the power to alter the fabric of reality itself. In the vast, cold depths of space, some stars are so dramatically stripped down over their lifetimes that they are reduced to nothing more than bare cores of carbon, pure elemental carbon untouched by other elements. When a star, similar in size and structure to our Sun, reaches the end of its life cycle, it undergoes a process of shedding its outer layers. This active shedding results in the creation of a dense core, which is often called a white dwarf. These stellar remnants are incredibly intriguing because some of them are primarily composed of carbon. Under the tremendous pressure exerted by their own gravity, so intense that it crushes their material into a compact sphere, this carbon can reach a state of crystalline excellence. To put it simply, certain white dwarfs transform into enormous celestial diamonds. These cosmic gemstones are roughly of the diameter of Earth, yet they are far more massive than our planet. The residual heat within them causes their surfaces to emit a faint glow, a gentle shimmer originating from the heat left over from their past fiery existence. Although these stars no longer engage in nuclear fusion, the process that traditionally powers stars, they continue to shine with a subdued luster that can last for billions of years before gradually cooling down and fading into an almost complete darkness. Interestingly, astronomers have observed that some white dwarfs exhibit what is known as pulsations, minute, rhythmic variations in brightness that resemble a kind of ringing, akin to the deep, resonant tone of a struck bell echoing through the void. Thus, in the vast, silent emptiness of space, there float crystalline remnants of ancient stellar fires, glowing, silent jewels drifting through the cosmos. They are no longer stars in the classic sense, but rather frozen echoes of stellar life, embodying the fiery history of the universe in their enduring, crystalline form. It's important to recognize that many aspects of the universe's extensive history have yet to unfold. For example, the Trinatsit Tochka Vosum billion years we consider as the universe's age seem to be a long, almost unimaginable span of time. But if we turn our gaze toward the entire future, the trillions of years that lie ahead, the perspective shifts dramatically. In this distant future, the processes we now take for granted, like star formation, galaxy assembly, or the flickering glow of black holes feeding on falling matter, will be a thing of the distant past. The stars, which now light up our night skies, will gradually fade away as their fuel runs out. The galaxies that now seem majestic and tightly bound will drift apart, carried away by the expanding fabric of space itself. Over immense spans of time, the universe will cool down, grow silent, and become a cold, vast, and seemingly empty expanse. However, it's crucial to understand that this grand, quiet, and lonely chapter of cosmic history has yet to begin. Today, we exist in a fleeting moment, a luminous, golden epoch, when the universe is alive and vibrant with motion, activity, and continuous change. This snapshot of cosmic vitality is a brief but beautiful flash in the long history of existence. While the past stretches far behind us, encompassing countless phenomena and events, the future stretches even farther ahead, infinity in scope, and is even more expansive in promise. Consider the remnants of supernova explosions, which continue to expand even thousands of years after the initial brilliance of the explosion has faded. When a massive star reaches the end of its life, it often ends with one of the universe's most spectacular events, a supernova. This explosive outburst can momentarily outshine an entire galaxy, emitting an intense burst of light that rivals the brightness of billions of stars combined. But the explosion itself is only part of the story. The shock wave created by this blast travels outward at incredible speeds, spreading across space for many centuries or even thousands of years, sweeping up gas, dust, and any debris caught in its path. These expanding shells of cosmic debris are what astronomers call supernova remnants. Such remnants glow across many wavelengths: radio waves, X-rays, visible light, each revealing different aspects of the explosion's history. Some form delicate, filamentary structures that resemble intricate lacework, while others appear as turbulent, cloud-like formations swirling chaotically through space. An example of these remnants is the Crab Nebula, a luminous, expanding cloud still stretching outward from the supernova explosion observed on Earth nearly 500 years ago, in the year 1154. These clouds, or remnants, are the slow exhalations of dying stars, revealing, long after the initial flash, the enduring aftereffects of catastrophic death. In addition to the dramatic explosions, tiny gravitational effects can subtly influence how we perceive distant light, even a single planet. And that subtle twist in perspective is all it takes to declare simply, "I am here." This statement might seem straightforward, yet it encapsulates a profound truth about our position within the vast cosmos. Long ago, the universe shone with an intense, almost blinding shade of orange, a luminous glow that once bathed all of existence in fiery brilliance. In the earliest moments following the cataclysmic event known as the Big Bang, the universe was a seething, dense plasma, radiating with an almost unimaginable heat and brightness. During these initial instants, everything was in a state of extreme compression and high energy, creating a blinding light that illuminated the very fabric of space. But as the universe began to expand, spreading outwards in a grand cosmic growth, this immense glow gradually diminished in intensity. The expansion caused the universe to cool over time, much like a pot of boiling water, gradually losing heat as it boils away. As temperatures dropped, approximately around 3000 Kelvin, the universe reached a pivotal moment when the first atoms could finally come into existence: simple, lightweight hydrogen and helium particles. This was a turning point in cosmic history. It marked the moment when light could once more travel freely throughout space, unhindered by the dense plasma. If one could have observed the universe at that precise epoch, it would have appeared a gentle, soft, orange-tinted radiance, an expansive, warm glow filling every inch of space, not the dark, star-studded night we see today, but something more akin to a comforting ember glowing from within the vast darkness. This primordial light, which we now recognize as the cosmic microwave background, has since been stretched and cooled by the ongoing expansion of the universe itself. As space expanded, the wavelength of this ancient radiation was lengthened, transforming from a bright, fiery glow into a faint, microwave shimmer that persists to this day. It is a faint, distant echo of the universe's earliest luminous phase, a relic from a time when the cosmos emitted an orange glow, an internal radiance that once illuminated everything in sight, now stealthily fading into the vast silence of time. However, the universe's cooling process has not been uniform across every region. Certain areas, containing more matter or trapped light, have retained their heat longer than others. Imagine a sprawling cosmic oven gradually turning off. As it cools, some parts remain warm for billions of years, while others are more quickly chilled. For instance, clusters of galaxies are enveloped in hot, glowing gas that continues to radiate heat centuries into cosmic history, sustaining their warmth far beyond the initial cooling. Conversely, other regions of space, more isolated or less dense, experience a more rapid decline in temperature, cooling more swiftly and becoming colder, faster. These temperature discrepancies influence how structures form within the universe. They impact the evolution of stars, the birth of new galaxies, and the duration of various cosmic phenomena. Even though the universe operates under seemingly simple physical laws, these local variations introduce a complex, textured universe. Warm pockets, where heat lingers slightly longer, small delays in processes unfolding across the great cosmic tapestry. The universe's cooling method is not like the precise mechanical cooling of a machine, but rather akin to weather, uneven, irregular, and quietly dynamic, with each region having its own pace of change. This ongoing, uneven cooling produces a universe that is textured and alive in its own subtle way. From this evolving cosmic fabric, the tantalizing possibility remains that one day, a new universe might be born within the old, emerging through mechanisms still shrouded in mystery. Some cosmological theories hypothesize that universes could generate new creations within our own universe, perhaps through quantum fluctuations, black holes, or other unknown processes. Such events would likely occur far beyond our observational reach, deep in the depths of space and time, making direct detection currently impossible. Yet, theoretically, we might recognize signs: a sudden swelling bubble, a nascent opening in space-time, indicating the birth of something altogether new, driven by unfamiliar physics disconnecting from our familiar reality. Whether such cosmic births have already occurred or will happen in the future remains an open question. We don't yet know if these events have ever taken place or if they are destined to happen someday. Still, the notion persists that somewhere in the quiet darkness of the universe, a new beginning could ignite from the end of something beautifully finite, a whisper within a silence, a fresh universe emerging from an ancient, quiet tomb. The universe continues to echo from its earliest moments, resonating with vibrations that persist through the eons. A fraction of a second after the Big Bang, The universe expanded explosively in a process known as inflation. This rapid, immeasurably swift expansion left behind delicate ripples, tiny quantum fluctuations that stretched across the fabric of space itself, like the first faint strokes of a cosmic symphony. These ripples became the foundational seeds for all future cosmic structures, galaxies, stars, planets, and everything in between. Furthermore, among the countless astonishing facts that the universe holds within its vastness, one of the most quietly extraordinary truths perhaps lies in a simple yet profound realization. You are essentially woven from the very fabric of the cosmos itself. The elements that compose your body, carbon, the backbone of organic life, calcium, vital for your bones, iron, coursing through your bloodstream, have all been forged amid the fiery hearts of ancient stars. These elements were not simply created out of nowhere. They were born deep within nuclear reactions, then scattered across the immense reaches of space. Over eons, these cosmic seeds eventually gathered, forming the building blocks of planets, ecosystems, and life itself. In this grand, luminous process, you are not separate from the universe. Instead, you are a direct expression of its ongoing cycle of birth, death, and rebirth. In a sense, you embody a fleeting, conscious moment of the universe's endless unfolding. You are like a spark of awareness, a conscious flickering within an otherwise vast and impersonal expansion of matter and energy. The universe, in its infinite grandeur, merely moves, shines, cools, and transforms without recognition or reflection. Yet, through the existence of conscious beings like yourself, it has acquired the remarkable ability to see itself. As you gaze inward and outward, the universe appears to grow eyes, watching and pondering its own vastness through you. These inner eyes, born from stardust, look out onto the cosmos, marveling at its own complexity, contemplating its origins, and even dreaming of itself in the process. Even as you begin to drift toward slumber, the universe continues its silent, eternal dreaming. It weaves its stories through the crackle of distant quasars, the glow of ancient galaxies, and the faint whispers carried across the fabric of space-time. As you listen to the faint echoes from the dawn of creation, from the first moments when the universe unfolded from a singular point, you are participating in a universe that is still alive with stories and secrets. Somewhere within this cosmic symphony, amongst the light of centuries-old stars and the quiet stillness between galaxies, there exists a gentle breath, yours. That slow, calming breath, softly released, echoes the universe's quiet harmony, while your thoughts soften and your mind begins to rest. Perhaps you have already fallen asleep, carried by the rhythm of distant cosmic waves, lost in the universe's timeless lullaby. This universe is a beautiful paradox, brimming with motion and intrigue, yet also bathed in profound stillness. It is a place where heat, light, and gravity generate storms and eruptions, constantly transforming everything within it. Yet, amidst all this relentless activity, there is also an underlying peace, an unspoken calmness that pervades the void between stars and across galaxies. It holds within it not only fiery energy, but also a tranquil serenity, a space where silence and quietude reign supreme. The extraordinary truth is that we can find pieces of this peace, moments of stillness and understanding, simply by observing and contemplating the universe with patience and serenity. The capacity to know and experience this peacefulness, even in fleeting moments, is what makes it so remarkably beautiful. Wherever you find yourself in this moment, whether fully awake, aware of your surroundings, or gently slipping beyond the reach of thought, may your dreams tonight be soft and kind. May your body rest as peacefully as starlight, gently resting upon the calm waters of a serene lake. And let your consciousness, even if only faintly, carry the memory of a universe that glows with life and mystery, not just in the vast night sky above you, but deep within your own being. Remember that this universe, in all its grandeur and stillness, exists within you as well. If, at this moment, you are still awake and alert, you are welcome to continue exploring the deeper stories of the cosmos, perhaps starting the next chapter of this grand journey. And if you wish to drift into restorative sleep, surrounded by gentle tales of wonder and awe, know that there are endless such stories waiting to be told, one peaceful soul at a time. Each night offers a new opportunity to connect with the silent, awe-inspiring world around and within us all. Now, may you find your peaceful rest. Good night.